Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're setting out for a place that sounds as though it belongs in a storybook rather than a scientific catalogue. A world where sunsets come in pairs, where shadows might stretch in more than one direction, and where looking up into the sky could reveal something humans once believed existed only in fiction. For most of us, the sun is such a familiar companion that we rarely stop to think about it. It rises, it shines, it sets, and it quietly organises our lives without asking for much recognition. Every morning begins with one sunrise, every evening ends with one sunset. One star governs the sky. But what if that wasn't true? What if dawn arrived twice? What if a second sun appeared beside the first, painting the landscape with an entirely different kind of daylight? What would it feel like to stand beneath a sky that belonged to two stars instead of one? Before we begin, I'd love to ask the same gentle question I often do. Where in the world are you listening from tonight? Is it late evening, early morning? Perhaps you're already tucked into bed while the rest of your household sleeps. Maybe you're listening during a quiet moment after a long day. Wherever you happen to be, and whenever this finds you, I'm glad you're here. And if you find this journey soothing, interesting, or simply a pleasant way to unwind, I'd be ever so grateful if you liked the video and subscribed. It helps this little corner of calm reach fellow travellers who enjoy drifting off while contemplating the universe. Now then, settle in, relax your shoulders, and allow your thoughts to slow down. Because tonight we're travelling more than 200 light years from Earth to visit a world that changed astronomy forever. Its name is Kepler-16b, and it is the planet with two suns. The idea sounds strangely familiar, doesn't it? Even if you've never heard the name Kepler-16b before, chances are you've imagined something similar. For decades, perhaps even centuries, people have wondered what it would be like to live beneath multiple suns. Writers imagined it, artists painted it, storytellers filled distant worlds with twin stars hanging over alien deserts. The concept feels almost magical because it breaks one of the assumptions we rarely question. One world, one sun, simple, comfortable, predictable. Yet the universe has a habit of ignoring our expectations. Again and again, whenever humanity decides something seems too unusual to be real, the cosmos quietly replies, "Actually, let me show you something." And that's exactly what happened here. Kepler-16b is not a fantasy. It is not a science fiction invention. It is a genuine planet orbiting a pair of stars in a distant solar system. Astronomers discovered it in 2011, and when they did, it immediately captured the imagination of people around the world. Because suddenly a place resembling those fictional double-sun worlds actually existed. Not in a movie, not in a novel, not in an artist's imagination. Out there among the stars, real. To appreciate just how remarkable that is, it helps to start with our own cosmic neighbourhood. Earth orbits a single star, Mercury does too. Venus, Mars, Jupiter, Saturn, Uranus, Neptune. All of them travel around the same sun. Our solar system is built around one central source of light and heat. For a long time, scientists naturally assumed this arrangement was common. After all, it worked perfectly well. Why complicate things? Yet when astronomers began studying the galaxy more carefully, they discovered something surprising. Single stars like our Sun may not actually be the norm. In fact, many stars belong to pairs. Some exist in groups of 3. Others form even larger systems. 2 stars orbiting each other are known as a binary star system. And binary systems are astonishingly common throughout the Milky Way. Imagine looking up at the night sky from another planet. To your eyes, what appears to be one bright star may actually be 2 stars locked in an endless gravitational dance around each other. The galaxy is full of such partnerships. For generations, however, astronomers weren't sure whether planets could comfortably exist in these environments. After all, Having one star is complicated enough. Stars exert gravity. Gravity shapes orbits. Introduce a second star, and suddenly everything becomes much messier. Would planets be thrown out of the system? Would their orbits become unstable? Could a world survive billions of years while two suns tugged at it from different directions? These questions lingered for decades. Some computer models suggested it might be possible. Others suggested planetary systems would become chaotic. The truth remained uncertain. Then technology improved. Powerful telescopes began searching for planets around distant stars. Thousands of exoplanets were discovered. Each new finding expanded our understanding of what kinds of worlds could exist. Some planets turned out to be larger than Jupiter. Others were scorching hot. Some orbited their stars in just a few days. A few seemed bizarre enough to challenge everything scientists thought they knew. Yet Kepler-16b stood apart. Because it wasn't merely unusual. It answered a question that had fascinated astronomers for years. Can a planet orbit two suns? The answer turned out to be yes, and that answer opened an entirely new chapter in our understanding of planetary systems. But before we dive deeper into the science, let's spend a moment imagining what such a world might actually feel like. Suppose, somehow, you could stand on solid ground beneath a sky governed by two stars. The first thing you'd notice would be the light. Not necessarily brighter, just different. On Earth, sunlight arrives from a single direction. Every shadow points away from the sun. Trees cast one shadow. Buildings cast one shadow. You cast one shadow. It's such an ordinary feature of daily life that we barely notice it. Yet on a world with two visible suns, shadows become more complicated. Depending on the positions of the stars, you might see two overlapping shadows stretching across the ground. One dark, one faint. Both moving slowly as the sun shifted through the sky. The landscape itself would feel subtly unfamiliar. Your brain, trained by a lifetime beneath a single star, would constantly notice that something wasn't quite the same. Then there would be sunrise. On Earth, sunrise is relatively straightforward. The sun appears, the sky brightens, day begins. A double star system can create much stranger possibilities. Perhaps one star rises first. A soft dawn begins. Then a second sunrise follows later. The sky brightens again. Hours afterward, one sun might set while the other remains visible. Daylight could linger in unexpected ways. Twilight might behave differently. Even the colours of the sky could change depending on the characteristics of the stars involved. It's the sort of environment that would feel endlessly fascinating. You might spend years simply watching the sky. Of course, Kepler-16b itself is probably not the ideal vacation destination. We'll eventually discover why. But the principle remains extraordinary. A planet orbiting two stars demonstrates just how creative nature can be. Human beings often assume the universe follows familiar patterns because those patterns surround us. We see one moon, we orbit one sun, we experience one sunrise, so we unconsciously treat those arrangements as normal. Yet, normal is a dangerous word in astronomy. The moment scientists start believing something is normal, a telescope usually discovers an exception. That's part of what makes astronomy so enjoyable. The universe keeps surprising us. It refuses to stay inside neat categories. Even our own solar system contains enough oddities to fill entire libraries. A planet that rotates on its side. A moon with underground oceans. A world raining methane. A dwarf planet accompanied by multiple moons. And that's just our local neighbourhood. Once we look beyond the solar system, things become even stranger. Astronomers have discovered planets made largely of gas. Planets larger than expected. Planets smaller than expected. Planets orbiting dead stars. Planets surviving conditions that seem almost impossible. Kepler-16b joined this growing collection of cosmic surprises, not because it was the largest, not because it was the hottest, not because it was the most Earth-like, but because it demonstrated something profound. Planetary systems are more adaptable than we once imagined. Nature can build stable worlds, even in places that initially appear chaotic. 2 stars might seem like a recipe for orbital disaster, yet Kepler-16b calmly circles both of them, year after year, century after century, million year after million year. Its orbit remains remarkably stable. The planet doesn't care that humans once doubted its existence. It simply follows the path gravity has carved for it. There's something oddly comforting about that. Sometimes reality turns out to be more imaginative than fiction. A child might draw a picture of 2 suns in the sky. An adult might smile and call it fantasy. Meanwhile, somewhere far away, Kepler-16b quietly proves the drawing was not entirely wrong. The galaxy contains places stranger than our imaginations can easily invent. And that's before we even begin examining the stars themselves, because the stars of the Kepler-16 system are every bit as important as the planet. After all, Kepler-16b is not orbiting 2 identical suns. Its stellar companions are quite different from each other. They move in a continuous gravitational dance circling a shared centre of mass while the planet travels around both of them. Visualizing this arrangement takes a little practice. Our brains naturally picture planets orbiting one central object. That's what we've known our entire lives. But a binary system operates more like a cosmic dance floor. The stars move, the planet moves, everything influences everything else, and somehow, despite the complexity, the entire arrangement remains stable. Watching it from afar would probably be mesmerizing. The 2 stars would continually shift positions relative to one another, sometimes appearing closer together, sometimes farther apart, sometimes creating particularly striking alignments. Every day, every season, every year could bring subtle changes to the sky. A resident of such a system would likely develop an entirely different relationship with the heavens. Here on Earth, we can predict the sun's behaviour with extraordinary precision. Tomorrow's sunrise is easy to calculate. Next month's sunset is easy to calculate. The patterns are familiar, reliable, comforting. A double-star sky would encourage a slightly different perspective. Not chaotic, not random, just more intricate. A little richer in motion, a little more dynamic, and perhaps a little more beautiful. As the evening grows quieter and your thoughts begin to settle, it's worth reflecting on how recently humanity learned any of this. For most of history, Kepler-16b was completely unknown. No one knew it existed. No telescope had seen it. No astronomer had measured it. The planet spent billions of years orbiting its twin suns without a single human being aware of its presence. Then, in the span of just a few decades, our technology improved enough to detect it. That's a remarkable achievement when you stop and think about it. A species living on a small rocky planet around one star somehow learned to identify another planet, orbiting 2 different stars hundreds of light years away. Not by visiting, not by photographing oceans or mountains, simply by observing tiny changes in starlight. It's one of the quiet triumphs of modern astronomy. Long before astronomers discovered Kepler-16b, long before powerful space telescopes scanned distant stars for hidden planets, and long before anyone understood how worlds could orbit 2 suns at all, humanity was already imagining them. That may sound surprising at first. After all, when we think about scientific discoveries, we often imagine facts arriving before stories. We picture scientists uncovering something new, and then writers, artists and dreamers building ideas around it afterward. Yet the relationship is often the reverse. Human imagination tends to arrive first. Reality catches up later. The concept of twin suns belongs firmly in that category. Thousands of years before anyone knew that a real planet orbited 2 stars, people were already wondering what such a sky might look like. Not because they had evidence, not because they possessed advanced telescopes, but because humans have always looked upward and asked a very simple question. What if? That question may be one of the most powerful forces in history. It built ships, it built telescopes, it built observatories, and eventually it helped lead astronomers toward discoveries like Kepler-16b. But tonight, before we return to the science itself, let's spend some time exploring the long human fascination with multiple suns. Because the story of Kepler-16b didn't truly begin in 2011. In a way, it began thousands of years earlier when ancient people first started studying the sky. For most of human history, the heavens were not viewed as a collection of distant physical objects. They were stories. The sun was not merely a star. The moon was not merely a satellite. The planets were not merely worlds. They were characters, gods, messengers, symbols. Every culture developed its own interpretations. Ancient civilizations observed the regular movements of celestial bodies with extraordinary care. Farmers depended upon seasonal cycles. Sailors depended upon navigation. Priests depended upon calendars. The sky mattered a great deal. Because of that, unusual celestial events often carried enormous significance. Comets inspired fear. Eclipses inspired awe. Bright planets inspired myths. And occasionally people reported seeing what appeared to be multiple suns. Now, before we get too excited, these observations were not evidence of actual twin star systems visible from Earth. Instead, many were caused by atmospheric phenomena. One particularly beautiful example is called a sundog. Despite its somewhat amusing name, a sundog can be spectacular. When sunlight passes through ice crystals suspended high in the atmosphere, bright spots can appear on either side of the sun. To an observer unfamiliar with atmospheric optics, it can genuinely look as though multiple suns have appeared in the sky. Ancient records from various cultures describe such events. Imagine standing outside thousands of years ago. You look upward. Instead of one sun, you suddenly see 3 brilliant lights. No weather forecast explains it. No science textbook explains it. No internet forum discusses it. You're left with only your imagination. Naturally, stories would emerge, and they did. Throughout history, reports of extra suns often became woven into mythology and folklore. Ancient Chinese records contain descriptions of multiple suns appearing in the heavens. Greek writers documented unusual solar phenomena. Medieval chroniclers occasionally recorded mysterious celestial displays that frightened entire communities. Many of these accounts almost certainly described atmospheric effects rather than actual stars. Yet they reveal something important. The idea of more than one sun never seemed entirely impossible to the human mind. People were ready to imagine it. In fact, some cultures went much further. One of the most famous examples comes from Chinese mythology. According to an ancient legend, there were once 10 suns. These suns were often depicted as golden birds resting in a giant tree. Normally, only one crossed the sky at a time. But one day, all 10 emerged together. The earth began to scorch. Rivers dried up. Crops failed. The world suffered beneath unbearable heat. Eventually, a legendary archer named Hao Yi shot down 9 of the suns, leaving only one behind. The story served many purposes. It explained extreme heat. It celebrated heroism. It conveyed cultural values. Yet it also demonstrates how naturally people imagined skies containing multiple suns. The concept felt dramatic, powerful, memorable, and importantly, understandable. Even without scientific knowledge, ancient storytellers grasped that additional suns would radically transform life. More light, more heat, different seasons, different challenges. Those are exactly the kinds of questions modern astronomers ask when studying binary star systems. The tools have changed. The curiosity remains remarkably similar. Greek mythology offered its own solar narratives. The sun was often personified through Helios, later associated with Apollo in popular tradition. Stories describe the sun crossing the sky in a radiant chariot. While Greek myths didn't commonly feature permanent twin suns, they frequently explored unusual celestial events and cosmic disruptions. Many ancient cultures shared a fascination with changes in the heavens. A sky behaving differently was never treated casually. It demanded explanation. Because humans instinctively notice patterns. When those patterns break, stories rush in to fill the gap. You can see this tendency throughout history. People observe something unusual. They ask why. Then they create narratives. Sometimes those narratives become myths. Sometimes they become scientific hypotheses. The difference often depends on the tools available at the time. A Bronze Age farmer and a modern astrophysicist may appear very different. Yet both begin with the same basic reaction: curiosity. The farmer sees an unusual light in the sky and wonders what it means. The astrophysicist sees an unusual signal from a telescope and wonders what it means. Both are trying to make sense of the universe. As centuries passed, humanity's understanding of astronomy gradually improved. The Earth was recognized as a planet. The Sun became understood as a star. The planets were revealed as worlds. Scientific thinking increasingly replaced mythological explanations, yet the dream of multiple suns did not disappear. If anything, it became stronger. By the 19th century, astronomers had begun discovering binary star systems in large numbers. Powerful telescopes revealed that many stars existed in pairs. This realization transformed scientific thinking. Suddenly, twin suns were not fantasy. Twin stars were demonstrably real. You could observe them, measure them, calculate their orbits. The question shifted. Instead of asking whether two suns could exist, astronomers began asking whether planets might exist around them. That was a much harder problem. At the time, nobody knew. Planetary science itself remained young. No exoplanets had yet been discovered. Scientists didn't even know whether planets around other stars were common. Yet speculation flourished, and where science hesitates, fiction often charges ahead. The 20th century became the golden age of imagined double-sun worlds. Writers embraced the concept enthusiastically. After all, a sky with two suns immediately captures attention. It feels alien, exotic, different. A single image communicates that you are somewhere far from Earth. Science fiction authors understood this perfectly. One of the most influential examples arrived in 1941. Writer Isaac Asimov published a story called Nightfall. The premise was unforgettable. The story took place on a planet illuminated by multiple suns. Because at least one sun was always visible, the inhabitants had never experienced true darkness. Imagine that for a moment. No nighttime, no stars, no Milky Way, no moonlit evenings, generation after generation living beneath constant daylight. Then astronomers in the story predict something terrifying. An eclipse is coming. Darkness will fall for the first time in centuries. The result is panic. Civilization struggles to comprehend what the night sky truly contains. While the details differ greatly from Kepler-16b, the story demonstrates humanity's fascination with alternative skies. We're endlessly intrigued by environments that challenge our assumptions. A world with no night, a world with two suns, a world with three moons. Each forces us to reconsider what we take for granted. Then came perhaps the most famous twin sun image in modern culture. Even people who know almost nothing about astronomy recognize it. A lone figure stands on a desert world. Two suns sink toward the horizon. The sky glows orange. The moment is quiet, reflective, memorable. When audiences first saw that scene in Star Wars during 1977, it instantly became iconic. The world was called Tatooine. For millions of people, it represented the definitive double-sun planet. The image resonated because it felt simultaneously strange and believable. Not magical, not impossible, simply different. A variation on reality. For decades afterward, Tatooine became shorthand for any world orbiting twin stars, and interestingly, when astronomers eventually discovered Kepler-16b, many journalists immediately compared it to Tatooine. The nickname appeared everywhere. Newspapers used it, television programs used it, scientists themselves occasionally referenced it. The comparison helped ordinary people understand why the discovery mattered. You didn't need to understand orbital mechanics. You didn't need to understand transit photometry. You only needed to recognize one idea. A real-world version of a double-sun planet existed. That realization generated excitement far beyond astronomy circles, and perhaps that excitement reveals something important about human nature. We love discovering that reality is larger than expected. Think about it. Kepler-16b wasn't discovered because scientists were trying to validate science fiction. They were simply studying stars, collecting data, analyzing measurements, following evidence. Yet when the discovery arrived, it felt strangely familiar, almost as though imagination had prepared us for it. This relationship between imagination and science appears repeatedly throughout history. Submarines appeared in fiction before they became practical realities. Space travel appeared in fiction before rockets existed. Artificial intelligence appeared in stories long before computers became commonplace. Of course, imagination is often wrong. Countless fictional ideas never materialize. But occasionally reality surprises us by agreeing. Not perfectly, not exactly, just enough to make us smile. Kepler-16b belongs in that category. The actual planet differs enormously from fictional desert worlds. We'll eventually explore those differences, yet the central idea survived. A planet orbiting two suns, real, observable, measurable, existing independently of our stories. That's what makes astronomy so rewarding. The universe doesn't care what we expect. It simply exists. Sometimes that means reality disappoints our fantasies. Sometimes it exceeds them. In the case of Kepler-16b, it arguably did both. The planet isn't a comfortable desert world where people can walk beneath twin sunsets, but it is a genuine example of a phenomenon many people once considered purely fictional, and that's arguably even more impressive, because nature accomplished it without trying to entertain anyone. The system formed naturally. Gravity assembled it. Physics maintained it. The stars and planet have been performing their cosmic dance for billions of years. Long before human civilization emerged, long before myths were told, long before telescopes were built, long before anyone imagined Tatooine, the system was already there, circling quietly through the galaxy, unaware that one day a species on a distant planet would discover it and feel a sense of wonder. That thought alone can be strangely comforting. The universe contains realities waiting to be found. Some will surprise us, some will challenge us, some will seem almost familiar, as though they step directly from our collective imagination. Kepler-16b happens to be one of those rare discoveries. It feels simultaneously new and ancient. New because humanity only recently found it. Ancient because the dream of twin suns has existed for thousands of years, yet imagination can only take us so far. Eventually, curiosity demands details. Stories ask one question, science asks another. Not merely, could such a world exist? But rather, what exactly is it? Several hundred light years from Earth, a planet circles two stars in a steady gravitational dance. Today, astronomers call it Kepler-16b. News headlines often call it the real-life Tatooine. Scientists describe it as a circumbinary planet, meaning it orbits around two stars instead of one. Yet for most of human history, nobody knew it existed. No telescope had seen it. No calculation had revealed it. No story had named it. The planet spent billions of years quietly orbiting its twin suns, while Earth went through its own extraordinary journey. Dinosaurs appeared and vanished. Continents drifted. Civilizations rose and fell. Entire languages were born and disappeared. Meanwhile, Kepler-16b continued its orbit completely unnoticed. Then, in the early 21st century, humanity built a machine capable of finding worlds around distant stars. And everything changed. To understand how Kepler-16b was discovered, we need to begin with a spacecraft that never actually travelled anywhere particularly far. Unlike the Voyager probes, which journeyed toward the edge of the solar system, this spacecraft spent its entire mission observing a small patch of sky. Its name was Kepler, and it became one of the most successful planet hunters in history. When the Kepler Space Telescope launched in 2009, astronomers were already fairly confident that planets existed around other stars. The first confirmed exoplanets had been discovered years earlier, but finding them remained difficult. Stars are incredibly bright. Planets are incredibly faint. Trying to directly photograph an Earth-sized planet beside a star is a little like trying to spot a firefly hovering next to a lighthouse from thousands of kilometers away. The lighthouse dominates everything. The firefly practically disappears. So astronomers needed a different strategy. Instead of trying to see planets directly, they decided to watch stars very carefully. If a planet happened to pass in front of its star from our point of view, the star would become ever so slightly dimmer. Not by much, just a tiny reduction in brightness. Then, after the planet moved away, the star would return to normal. If the dimming happened repeatedly at regular intervals, it could indicate that a planet was orbiting the star. This technique is called the transit method. It sounds simple. In practice, it requires extraordinary precision. The changes in brightness can be incredibly small. Imagine watching a distant lighthouse and trying to notice when a tiny insect briefly flies across the beam. That gives you some idea of the challenge. Kepler was designed specifically for this task, day after day, month after month, year after year. The spacecraft monitored more than 150,000 stars simultaneously. It measured their brightness with astonishing accuracy. Most stars remained steady. Some fluctuated naturally. A few revealed signs of planets. And occasionally, astronomers encountered something truly unusual. One of those unusual stars carried the designation Kepler-16. At first glance, it wasn't particularly famous. It appeared as just another distant stellar system among thousands being monitored. Yet the light coming from it behaved in a very interesting way. The reason was simple. Kepler-16 was not a single star. It was a binary system, two stars orbiting one another. This immediately complicated things. When astronomers study a single star, planetary transits tend to follow relatively predictable patterns. A planet passes in front. The star dims. The cycle repeats. Binary stars are different. Two stars are constantly moving around each other. Their positions change. Their combined brightness changes. The geometry becomes much more complicated. Imagine trying to analyze the movement of a dancer. Now imagine trying to analyze two dancers moving around each other while a third dancer circles both of them. That's closer to the challenge astronomers faced. Fortunately, scientists enjoy complicated puzzles. In fact, many become scientists precisely because they enjoy complicated puzzles. The Kepler team began carefully examining the data. What they saw was fascinating. The two stars repeatedly eclipsed one another. One star passed in front of the other, then later the second star passed in front of the first. These eclipses created predictable changes in brightness. Nothing unusual there. Binary stars do this all the time. But something else appeared in the data. Additional dips in brightness. Unexpected ones. And those dips did not fit the pattern produced by the stars themselves. Something else seemed to be moving through the system. At this point, astronomers became interested. Very interested. Because strange signals often lead to important discoveries. Sometimes they turn out to be errors. Sometimes they reveal previously unknown phenomena. The challenge is determining which. Careful analysis followed. Scientists compared observations, they ran simulations, they tested various explanations. Could the signal be instrumental noise? Could it be a statistical fluke? Could it be something unrelated to a planet? Gradually, the evidence pointed toward a remarkable conclusion. A planet was orbiting both stars, not one star. Both. The discovery team included astronomers from multiple institutions, and their analysis revealed something extraordinary. The planet was real, its orbit was stable, and it represented the first confirmed example of a secundary planet discovered through transits. That last detail is important. Scientists had long suspected such planets might exist. Theoretical models suggested they were possible, but suspicion is not confirmation. Astronomy advances through evidence. Kepler-16b provided exactly that. For the first time, researchers could point to a specific world and say, there it is. A genuine planet orbiting two suns. The announcement arrived in 2011. News spread rapidly. Scientists were excited. Journalists were excited. Science fiction fans were excited. Even people who normally paid little attention to astronomy found themselves intrigued. The reason was obvious. The discovery felt familiar. The public immediately connected Kepler-16b with fictional double-sun worlds. Newspapers began using comparisons to Tatooine. Television programs repeated the analogy. Social media embraced it. Suddenly, a somewhat technical astronomical discovery became understandable to millions of people. You didn't need to know astrophysics. You only needed one image, a world with two suns in the sky. Instantly, people understood why the discovery mattered. Yet scientists were excited for reasons that went far beyond popular culture. From a research perspective, Kepler-16b represented something extremely valuable. Evidence. Before its discovery, questions remained about how planets formed in binary systems. Many researchers wondered whether the gravitational influence of two stars might disrupt planet formation. Young planetary systems are already chaotic places. Dust collides, rocks merge, objects scatter. Gravity pulls everything in different directions. Adding a second star seemed likely to make the situation even more complicated. Some simulations suggested planets could form. Others suggested difficulties. Kepler-16b demonstrated that nature had solved the problem. Somehow, despite the complicated environment, a planet formed and survived. That realization expanded scientific thinking. Perhaps binary systems were more hospitable to planets than previously assumed. Perhaps entire populations of circumbinary worlds were waiting to be discovered. As it turns out, they were. After Kepler-16b, additional circumbinary planets began appearing in astronomical surveys. One by one, researchers identified new examples. Each discovery reinforced the same lesson. Planet formation is remarkably adaptable. Nature is often more creative than scientists expect. Of course, finding Kepler-16b was only the beginning. Once astronomers knew the planet existed, they wanted to learn everything possible about it. How large was it? How massive was it? How long was its year? What kind of orbit did it follow? Could it support life? Answering these questions required detailed observations. Fortunately, the transit method provides more information than one might expect. When a planet repeatedly crosses in front of its star, astronomers can estimate its size. The amount of starlight blocked during transit offers clues about the planet's diameter. Additional measurements reveal mass. Combining these values helps researchers estimate composition. Gradually, a picture of Kepler-16b emerged, and in some ways, it surprised people. Many members of the public imagined a rocky world, a place with deserts, mountains, twin sunsets, perhaps even alien civilizations. Reality turned out to be rather different. Kepler-16b is not a second Earth. It is not a desert planet. It is not a comfortable destination for future tourists. In fact, it resembles Saturn far more than our own world. Large, gaseous, cold. The discovery itself remained spectacular, but the actual planet looked very different from the fictional worlds that inspired the comparisons. That tends to happen in astronomy. Reality rarely follows Hollywood scripts, yet the truth is often more interesting. A real planet orbiting two stars doesn't need to resemble a movie set to be remarkable. Its existence alone is remarkable. Think about the challenge involved. Two stars orbit one another continuously. Their gravitational influence changes constantly. The planet must navigate this environment for billions of years. One might expect instability. One might expect chaos. Instead, Kepler-16b follows a stable path. Reliable, predictable, enduring. There is something quietly impressive about that. The universe often appears messy when viewed up close. Stars explode, galaxies collide. Black holes consume matter. Yet beneath that apparent chaos lie patterns. Orbits settle into stable arrangements. Systems find equilibrium. Gravity organizes complexity into structure. Kepler-16b is a beautiful example of that principle. Two stars dance around each other. A planet circles both. Everything remains balanced, not perfectly, not forever, but long enough for astronomers on a distant world to notice. The discovery also highlighted another important lesson. Sometimes finding something requires patience. The Kepler mission did not discover Kepler-16b during its first glance. Data had to be collected, analysed, reanalyzed, interpreted. Scientific discoveries often arrive this way. Popular culture occasionally portrays breakthroughs as sudden moments of revelation. A scientist looks through a telescope, gasps dramatically, and instantly changes history. Reality is usually quieter. Months of observation, years of preparation, countless calculations, careful verification. Then eventually a conclusion. The discovery of Kepler-16b followed that pattern. Not dramatic, not flashy, just rigorous science performed exceptionally well. And because of that work, humanity gained something precious. Knowledge, a new piece of reality, a world that moved from imagination into evidence. The moment scientists confirmed Kepler-16b, the universe became slightly larger. Not physically larger, of course. The universe did not expand because of the discovery, but our understanding expanded. Our map of reality gained another landmark. That's one of the joys of astronomy. Every new discovery reminds us that there are still places we've never seen, systems we've never studied, phenomena we've never imagined. Kepler-16b was once hidden among countless stars. Today it has a name, a measured orbit, a known history, and a permanent place in scientific literature. Yet even after the discovery, an important mystery remained. What exactly were the two stars like? Let's move a little closer to the heart of the Kepler-16 system. So far we've talked about the planet itself, the world that captured headlines because it circles two suns. We've explored humanity's long fascination with twin-star skies and followed the astronomers who finally discovered a real example of one. But now it's time to meet the stars themselves. Because while Kepler-16b receives much of the attention, it is really a supporting character in a much larger story. The true stars of the system are quite literally the stars, and unlike many science fiction portrayals of double-star worlds, the suns of Kepler-16 are not identical. In fact, if you could somehow visit the system and observe them up close, you would quickly notice that one dominates the partnership. The other plays a quieter role. Together, however, they create one of the most fascinating celestial dances ever discovered. To begin, it helps to remember something that isn't always obvious when we look at the night sky. Stars come in many different varieties. On Earth, we often think of stars as distant points of light that differ mainly in brightness. Some shine more intensely, some appear fainter. Yet that simple view hides tremendous diversity. Stars vary in size, they vary in mass, they vary in temperature, they vary in colour. Some are giant stars hundreds of times larger than the Sun. Others are tiny red dwarfs, barely massive enough to sustain nuclear fusion. Some burn blue-white and incredibly hot. Others glow with a cooler reddish hue. Even within our own galaxy, the differences can be astonishing. The Kepler-16 system contains two stars that belong to different categories. The larger of the pair is known as Kepler-16a. The smaller companion is called Kepler-16b. The names may not sound especially exciting, but astronomers tend to favour practicality over poetry. The important thing is what these stars actually are. Kepler-16a. A is the dominant member of the system. It possesses roughly 69% of the Sun's mass and around 65% of the Sun's radius. That means it is smaller than our Sun, but still substantial enough to serve as the system's primary source of light and heat. If you could place Kepler-16a beside our Sun, it would look noticeably smaller. Not tiny, not insignificant, just more modest. Think of it as a slightly reduced version of the star we know so well. Its surface temperature is lower than the Sun's, making it somewhat cooler and less luminous. Even so, it remains the heavyweight of the pair. Then there is Kepler-16b. This second star is considerably smaller. Its mass is only about 20% that of our Sun. Its radius is also much smaller. In astronomical terms, it belongs to the category known as a red dwarf. Red dwarfs are the most common stars in the Milky Way. In fact, they may account for the majority of stars in our galaxy. Ironically, despite being so common, they're difficult to see from Earth because they are relatively faint. The nearest star to our solar system, Proxima Centauri, is a red dwarf. Many of the stars surrounding us are red dwarfs. They simply don't stand out the way larger stars do. Kepler-16. B fits comfortably into that category. Compared to its larger companion, it produces much less light. If Kepler-16a is the lead singer in the band, Kepler-16b is more like the backup vocalist. Important to the performance. Not usually the centre of attention. Yet without it, the entire system would be fundamentally different. Now here's where things become particularly interesting. When most people imagine a planet orbiting two stars, they picture both stars sitting relatively still, while the planet circles around them. That isn't actually what happens. The stars themselves are constantly moving. In fact, Kepler-16a and Kepler-16b spend their entire existence orbiting each other. Imagine two dancers holding hands while spinning around a shared centre point. Neither dancer remains stationary, both move continuously. That's closer to reality. Gravity binds the two stars together. Each star pulls on the other. As a result, they perform an endless orbital dance that has likely continued for billions of years. One star does not simply sit at the centre, while the other circles around it. Instead, both stars revolve around a common centre of mass. Astronomers call this point the barycenter. It's an important concept because it appears everywhere in the universe. Even Earth and the Moon orbit a shared barycenter. The same is true for planets and stars. Nothing is truly motionless. Everything influences everything else. In the Kepler-16 system, this shared centre lies closer to the larger star because Kepler-16a contains much more mass. Still, both stars move. Neither can remain perfectly still. The result is a graceful cosmic dance that repeats over and over again. The stars complete one orbit around each other approximately every 41 days. That means if you somehow lived within the system and watched from a suitable location, the relative positions of the two stars would constantly change. Sometimes they would appear closer together, sometimes farther apart. Their arrangement in the sky would never remain exactly the same for long. This alone would create a dramatically different experience compared to life on Earth. Here, the Sun appears as a stable object. It rises, it sets. Its size in the sky remains essentially unchanged. Day after day, the pattern repeats. The Kepler-16 system introduces far more variety. The stars are always shifting position relative to one another. Their celestial choreography never truly stops, and because one star is brighter than the other, the visual effect would likely be fascinating. Imagine standing beneath a sky where a golden-orange sun dominates the horizon, while a smaller, dimmer companion drifts nearby. At times, they might appear relatively close. At other moments, they could separate noticeably. The sky would become a dynamic place, not chaotic, just continually changing. Of course, this raises an obvious question. How stable can such a system really be? After all, if the stars are constantly moving, wouldn't that create problems for the planet orbiting them? At first glance, it seems like it should. And this was one reason astronomers spent years debating whether circumbinary planets could exist. The gravitational environment appears complicated. Two stars pulling in different directions, a planet trying to maintain a stable orbit. The whole arrangement sounds like a recipe for instability. Yet nature has an advantage over human intuition. Nature doesn't care what seems complicated. If the laws of physics permit something, the universe may find a way to make it happen. And Kepler-16 is a perfect example. The stars orbit each other in a remarkably stable configuration. They've likely been doing so for billions of years. The planet, meanwhile, circles both stars at a safe distance. Everyone follows their assigned gravitational path. No collisions, no catastrophic ejections, just predictable motion governed by gravity. In some ways, it's similar to a carefully choreographed dance routine. From a distance, the movements may appear complicated. Look more closely, however, and patterns emerge. Everything has its place. Everything follows rules. The elegance becomes apparent. This realization often surprises people because astronomy sometimes presents the universe as violent and chaotic. And to be fair, parts of it certainly are. Stars explode, black holes consume matter, galaxies collide. The cosmos can be extraordinarily dramatic. Yet much of astronomy is actually about stability. Stable orbits, stable stars, stable systems lasting billions of years. The Kepler-16 stars belong to that quieter category. Their dance is not explosive, it is patient, steady, reliable. A performance measured not in minutes or hours, but in geological epochs. Think about that for a moment. Human civilization spans only a few thousand years. The Kepler-16 stars have likely been orbiting each other for billions. They completed their dance countless millions of times before Earth developed complex life. They continued dancing while dinosaurs ruled our planet. They continued dancing while humans learned agriculture. They continued dancing while telescopes were invented, and they will likely continue long after our current era becomes ancient history. There is something calming about that perspective. The universe operates on timescales so vast that even civilizations become brief moments. Yet despite those immense durations, the fundamental process remains surprisingly simple. Gravity pulls, objects move, orbits persist, the stars keep dancing. Another fascinating aspect of Kepler, 16a and Kepler-16b, is how astronomers were able to study them so precisely. Normally, measuring distant stars is difficult. Binary systems, however, provide unique opportunities. Because the stars periodically eclipse one another, scientists can gather enormous amounts of information. When one star passes in front of the other, the system's brightness changes. These changes reveal clues about size, mass, temperature, orbital period. Researchers can extract remarkable amounts of information from subtle variations in starlight. It's almost like solving a puzzle using shadows. No spacecraft has visited the system, no probe has flown through it. Yet astronomers know a tremendous amount about these stars, all because light carries information. That idea remains one of the most beautiful aspects of astronomy. Nearly everything we know about the universe arrives through light. The stars send photons across hundreds of light years. Those photons reach our instruments. Scientists decode the messages hidden within them. From tiny fluctuations in brightness, entire worlds emerge. Stars reveal their properties. Planets reveal their presence. The universe tells its story through light. Kepler-16. A and Kepler-16b are no exception. Their combined light allowed researchers to reconstruct the structure of the entire system, and that structure turned out to be extraordinarily valuable, because understanding the stars ultimately helps us understand the planet. After all, a world orbiting two stars experiences a very different environment than Earth does. The amount of light changes, the geometry changes, the appearance of the sky changes. Everything begins with the stars. They define the stage upon which the planet exists. Without understanding them, Kepler-16b remains incomplete. With them, the picture starts becoming clearer. We can begin imagining how sunlight behaves, how shadows move, how seasons might develop, how the sky might appear from a hypothetical moon orbiting the giant planet. Now that we've met the two suns and understand the gravitational partnership at the heart of the system, we can finally explore one of the most remarkable questions of all. How does a planet actually orbit two stars? A giant planet circles two stars with unwavering patience. One sun follows its own path. The second sun follows another. Both stars orbit each other continuously, never standing still for even a moment. And somehow, despite all that motion, despite all those competing gravitational influences, a planet remains locked in a stable orbit around both of them. At first glance, it sounds impossible, or at the very least, extremely complicated. Most of us grow up with a simple picture of how planetary systems work. There is a star in the centre, planets orbit around it, everyone follows their path, and life goes on. Our solar system fits that picture beautifully. Mercury circles the Sun, Venus circles the Sun, Earth circles the Sun, Mars circles the Sun. Every major planet follows the same basic arrangement. The Sun sits in the middle like the hub of a wheel. The planets travel around it, simple, predictable, comforting. So when people first hear about Kepler-16b, they often imagine something entirely different. Some picture a planet being pulled back and forth between two stars. Others imagine a chaotic orbit that constantly changes direction. A few imagine the planet somehow orbiting one star and then the other. The reality is much more elegant and surprisingly stable. To understand why, let's begin with gravity itself. Gravity is one of those things we experience every day without really noticing. It keeps our feet on the ground. It keeps oceans attached to Earth. It keeps the moon in orbit. It keeps planets moving around stars. In fact, gravity is the architect of almost everything large-scale in the universe. Stars form because gravity pulls gas together. Galaxies form because gravity gathers stars. Solar systems form because gravity organizes matter into predictable patterns. The universe is full of motion, but gravity provides much of the structure. Now imagine two stars forming close together. This happens quite often. As enormous clouds of gas collapse under their own gravity, multiple dense regions can develop within the same cloud. Instead of creating a single star, the process creates two. The newborn stars emerge relatively close to one another. Immediately, gravity begins linking their futures together. Neither star is strong enough to ignore the other. Neither star can simply remain stationary. Instead, they begin orbiting a shared centre of mass. The cosmic dance we discussed earlier begins. This arrangement is known as a binary star system, and binary systems are incredibly common. In fact, astronomers believe that a significant percentage of stars in the Milky Way belong to binary or multiple star systems. In other words, The situation we experience with one sun may not be the galaxy's default arrangement after all. That realization alone is fascinating. For thousands of years, humanity assumed our solar system represented a typical planetary system. Now we know nature enjoys far more variety than we once imagined. But here's where things become tricky. Young stars are surrounded by enormous disks of gas and dust. These disks are the birthplaces of planets. Tiny grains collide, small rocks form, larger rocks form, objects merge repeatedly. Eventually, planets emerge. At least that's the simplified version. The actual process is considerably messier. Imagine trying to build a city while every brick is moving at thousands of kilometers per hour. That's closer to reality. Planet formation is not neat. It's chaotic. Countless collisions occur. Objects are scattered. Some grow, some shatter, some get ejected entirely. Yet over millions of years, larger bodies gradually emerge. In a single star system, this process is already difficult enough. Introduce a second star, and things become significantly more complicated. Now, the gravitational environment changes constantly. The stars move. Their positions shift. The forces acting upon the surrounding material evolve continuously. For many years, astronomers wondered whether planet formation could even succeed under such conditions. The concern made sense. Imagine trying to stack blocks while standing on a floor that keeps moving beneath you. The task becomes harder, perhaps impossible. Similarly, many researchers suspected binary systems might interfere with planetary growth. The stars could stir the disk too aggressively. Collisions might become destructive instead of constructive. Young planets might be thrown from the system before they fully formed. These concerns weren't unreasonable. Gravity can be surprisingly disruptive. In our own solar system, Jupiter's immense gravity has shaped countless objects. Asteroids have been scattered, comets have been redirected, entire orbital regions have been altered. A second star seemed capable of causing even greater disturbances, yet nature had other ideas. Kepler-16b exists, which means planet formation succeeded. Not only did it succeed, but the resulting planet survived long enough for us to discover it. That fact alone tells us something important. The universe is remarkably good at finding stable solutions. At first glance, a binary system looks chaotic. Look more carefully, however, and stable patterns emerge. Let's visualize what actually happens in the Kepler-16 system. The two stars orbit each other every 41 days or so. They move continuously around their shared center of mass. Meanwhile, Kepler-16b remains much farther away. This detail is crucial. The planet does not orbit between the stars. It does not weave back and forth. It does not repeatedly switch allegiance from one sun to the other. Instead, it circles both stars together. Astronomers call this a circumbinary orbit. The word simply means around the binary. Think of it this way. Imagine two figure skaters spinning around each other in the middle of an ice rink. Now imagine a third skater circling both of them along the outer edge of the rink. The outer skater isn't trying to weave through the pair. They're simply orbiting the entire system. That's much closer to what Kepler-16b does. The planet treats both stars as a single gravitational destination. Not literally one object, of course. But from the planet's perspective, the stars function as a central pair around which it travels. This arrangement provides stability. The distance matters enormously. If Kepler-16b orbited too close to the stars, gravitational disturbances would become problematic. The orbit might become unstable. The planet could be ejected. It could crash into one of the stars, or it could end up following a highly erratic path. Instead, nature placed it safely beyond the danger zone. The planet circles at a distance where stable motion becomes possible. This concept appears throughout astronomy. Distance often creates order. Mercury survives because its orbit is stable. Earth survives because its orbit is stable. Moons survive because their orbits are stable. The same principle applies here. Kepler-16b occupies a gravitational sweet spot, not too close, not too far, just right. Astronomers sometimes refer to regions of orbital stability within planetary systems. These regions act like safe neighbourhoods. Objects inside them can survive for enormous periods of time. Objects outside them may face greater risks. Kepler-16b appears to reside in one of these stable zones, and it has likely remained there for billions of years. Think about what that means. Every orbit, every revolution, every journey around its twin suns, the planet follows essentially the same path, year after year, million year after million year, billion year after billion year. The stars continue their dance. The planet continues its journey. Gravity keeps everyone organised. This stability is actually one of the most remarkable aspects of the discovery. Many people focus on the dramatic image of two suns. Scientists were equally impressed by the orbital mechanics, because the existence of Kepler-16b demonstrated that stable circumbinary systems were not merely theoretical possibilities, they were real. Nature could build them, nature could maintain them. And perhaps most importantly, nature could build them more than once. After the discovery of Kepler-16b, astronomers found additional circumbinary planets. The galaxy clearly wasn't producing just one example. An entire category of planetary systems existed. Kepler-16b simply happened to be the first confirmed member that captured global attention. The discovery changed how researchers thought about planet formation. Beforehand, some models treated binary systems as unusually difficult environments. Afterwards, scientists began reconsidering those assumptions. Maybe planets form around binary stars more often than expected. Maybe stable orbits are easier to achieve than previously believed. Maybe the galaxy contains vast numbers of worlds illuminated by multiple suns. Every discovery generated new questions. That's one of the interesting things about science. Answers often create more mysteries than they resolve. Find one planet. Suddenly you want to know how many others exist. Discover a stable orbit. Suddenly you want to know how stability develops. Observe one binary system. Suddenly you want to compare hundreds. Knowledge expands outward. One question leads to another, then another, then another. Kepler-16b became part of that process. And its orbit remains one of the most compelling aspects of the system. Because while the mathematics behind orbital mechanics can become extraordinarily complex, the underlying idea is surprisingly approachable. Gravity seeks balance, objects respond, patterns emerge. The universe often behaves like a giant system of interconnected motions. Everything influences everything else, yet stability appears again and again. Consider our own moon. The moon is constantly falling toward Earth. Earth is constantly pulling on the moon. Yet because the moon is also moving sideways, it never crashes into our planet. Instead, it remains in orbit. The balance between motion and gravity creates stability. The same principle operates throughout the cosmos. Kepler-16b survives because gravity and motion remain balanced. Not perfectly, nothing in nature is perfectly static, but sufficiently balanced to endure for immense periods of time. And from the perspective of an observer standing somewhere within that system, the consequences would be fascinating. Imagine watching the sky over many months. The stars continually shift position relative to one another. Their dance changes, the lighting changes, the geometry changes. Yet the planet's overall path remains reliable. Its year proceeds, its orbit continues. The system evolves in predictable ways. It's a wonderful example of something astronomers frequently encounter. Complexity does not necessarily mean chaos. Sometimes incredibly complicated systems behave with remarkable order. A hurricane contains immense complexity, yet follows recognizable physical laws. A galaxy contains hundreds of billions of stars, yet exhibits large-scale structure. A binary star system may appear intimidating, yet stable planetary orbits can emerge naturally. Nature often achieves elegance through complexity rather than simplicity. Kepler-16b reminds us of that. The planet's orbit is not remarkable because it defies physics. It's remarkable because physics allows it. The same laws governing Earth, the Moon, and the planets of our solar system also govern Kepler-16b. Gravity does not change. The rules remain consistent. Only the arrangement differs, and that arrangement produces something extraordinary, a world illuminated by two suns. Of course, understanding the orbit is only part of the story. Knowing how the planet moves tells us little about what it might actually feel like to stand beneath such a sky. Because once you understand the mechanics, another question naturally appears. What would daily life look like beneath two stars? How would daylight behave? How would shadows move? What would sunrise actually feel like? Would the sky resemble anything familiar? Or would it seem completely alien? A clock hanging on your wall would not be particularly helpful on Kepler-16b. Not because clocks stop working. Not because physics behaves differently. But because almost everything we casually associate with the passage of time would feel unfamiliar. Here on Earth, we build our sense of time around patterns that have remained stable for millions of years. One sunrise, one sunset, a day lasting 24 hours, a year lasting roughly 365 days. The moon follows its cycle, the seasons follow theirs. Generation after generation, humanity has lived beneath those rhythms. They feel natural, obvious even. Yet they are only one possible arrangement among countless others. Travel to Kepler-16b and you would quickly discover that nature is perfectly capable of creating very different schedules. The planet itself circles its twin suns once every 229 Earth days. That means a complete year on Kepler-16b is considerably shorter than a year here. If somehow you could stand on a solid surface there and celebrate birthdays, you would celebrate them much more frequently. Of course, Kepler-16b itself is a gas giant, so standing directly on it would be an exceptionally bad idea for a variety of reasons that we'll discuss later. For now, however, imagine a hypothetical moon orbiting the planet. A large moon with a stable surface. A place where someone could actually look upward and watch the sky. What would life be like there? The answer begins with understanding that there would be two different kinds of motion constantly unfolding overhead. The first would feel somewhat familiar. The planet would rotate. Days would pass. The sky would brighten and darken. Stars would rise and set. Anyone living there would experience a daily cycle of light and darkness. But layered on top of that ordinary rhythm would be the motion of the two suns themselves. And that's where things become interesting. On Earth, the sun appears predictable. You know where to look. You know roughly where it will rise. You know roughly where it will set. Its behaviour changes slowly through the year. Kepler-16's sky would be much more dynamic. Remember, the two stars orbit one another every 41 days. They're constantly moving relative to each other. That means their positions in the sky would never remain fixed for long. Some mornings the stars might appear relatively close together. On other mornings they could be noticeably farther apart. The geometry would keep changing. A resident of such a world would likely pay far more attention to the sky than most of us do. After all, every sunrise could be slightly different. And that's something we rarely experience on Earth. Imagine stepping outside at dawn. The larger star begins climbing above the horizon. Its light spreads across the landscape, the ground brightens, shadows emerge. Everything feels relatively familiar. Then, sometime later, a second sun appears. Not another sunrise the following day, a second sunrise the same day. The smaller star rises separately. Its light joins the first. The landscape changes again. Brightness increases. New shadows appear. The entire character of daylight shifts. That alone would be an extraordinary sight. Most humans have spent their entire lives beneath one dominant source of daylight. Our brains are built around that experience. We instinctively understand how sunlight behaves. We know where shadows belong. We know how the sky should look. Introduce a second star, and many of those assumptions stop working. For example, let's talk about shadows. Shadows seem simple. They're so ordinary that we rarely think about them. Stand outside on a sunny afternoon, and you'll cast one shadow. A tree casts one shadow. A building casts one shadow. Everything follows the same rule: one sun, one shadow. A double star system changes that immediately. With two visible stars in the sky, objects could cast multiple shadows simultaneously. One shadow would be created by the larger star, another by the smaller star. Depending on the relative brightness of the stars, one shadow might appear darker while the other appears fainter. The effect would be subtle at times and dramatic at others. Imagine walking across a field while two versions of your shadow trail beside you. One slightly stronger, one slightly softer, both moving as the stars slowly shift positions overhead. It's the sort of thing that would probably stop tourists in their tracks. Residents, of course, would eventually consider it completely normal. That's another interesting aspect of life. Human beings adapt remarkably quickly. The strange eventually becomes ordinary. Think about Earth for a moment. We live on a giant rotating sphere hurtling through space at enormous speed. Our planet orbits a nuclear fusion reactor nearly 150 million kilometers away. The entire solar system moves through the galaxy. The galaxy itself moves through the universe. Objectively speaking, it's all quite bizarre. Yet because we're accustomed to it, we rarely think about it. The same would happen beneath the skies of Kepler-16b. Double shadows would eventually become routine. Twin sunsets would become ordinary. Children would grow up assuming that's simply how the universe works. Visitors from Earth would find it astonishing. Locals would wonder what all the fuss was about. Then there is the question of daylight itself. How bright would the sky actually be? The answer depends on where the stars happen to be in their orbital dance. Sometimes both stars might contribute substantial light simultaneously. At other times, one star could dominate. The intensity of daylight would vary in ways that Earth simply doesn't experience, not wildly from hour to hour, but enough to be noticeable. Imagine living in a place where the brightness of afternoon sunlight subtly changes depending on the current arrangement of two suns. Over time, people would likely learn to recognize those patterns instinctively. Farmers would notice them. Travelers would notice them. Anyone who spent enough time outdoors would become familiar with the rhythm. And rhythms matter. Human civilization has always organized itself around predictable cycles. The cycle of day and night. The cycle of seasons. The cycle of years. These patterns shape everything from agriculture to culture. A world orbiting two suns would develop its own unique rhythms, its own calendar, its own sense of time. In fact, calendars there might become surprisingly complicated. On Earth, our year is based primarily on one orbit around one star. Simple. Kepler-16b's environment introduces additional cycles. The planet takes approximately 229 Earth days to complete an orbit around the stellar pair. Meanwhile, the stars themselves complete their mutual orbit every 41 days. Those two clocks keep running simultaneously. Sometimes their cycles align in interesting ways, sometimes they don't. The result would be a sky that continually evolves. Patterns would repeat, but not always on the schedule you might expect. Imagine trying to predict exactly how the stars will appear 6 months from now. You wouldn't simply track the planet's orbit. You'd need to account for the stars' positions as well. It's almost like having multiple celestial clocks operating at once. Ancient astronomers on such a world would likely become experts in orbital cycles. Their calendars might be extraordinarily sophisticated, not because they enjoy complexity, but because the sky would demand it. Humans are excellent pattern recognition machines. Give us a complicated sky and sooner or later someone starts making charts. Someone starts recording observations. Someone starts developing astronomy. That would almost certainly happen there too. Another fascinating consequence involves eclipses. Here on Earth, solar eclipses are relatively rare. Everything has to align just right. The moon must pass between Earth and the sun at precisely the correct moment. When it happens, the result is spectacular. People travel across continents to witness it. Entire communities gather to watch. The event becomes a memory that lasts a lifetime. In a binary star system, eclipses can occur more frequently. Not necessarily total eclipses like the ones we experience. Different types of eclipses. The stars themselves periodically pass in front of each other. The larger star can partially obscure the smaller can cross in front of the larger. From the perspective of a hypothetical observer, these events could alter the amount of daylight reaching the world. Imagine a perfectly normal afternoon. Then, gradually, one star begins crossing in front of the other. The sky doesn't become dark. Day doesn't suddenly end. Instead, the quality of light changes. Brightness subtly shifts. Shadows soften. The entire landscape takes on a slightly different appearance. Such events might become familiar features of the calendar. Children could grow up looking forward to them. People might plan festivals around them. Entire cultural traditions could emerge. It's worth remembering that humans attach meaning to celestial cycles remarkably quickly. Our own history demonstrates this repeatedly. Solar events, lunar events, planetary alignments, comets, meteor showers. Whenever the sky exhibits predictable behavior, people tend to notice. Then they build traditions around it. A civilization beneath two suns would likely do the same. Of course, not every aspect of daily life would feel exotic. Many things would remain surprisingly familiar. Gravity would still pull downward. Weather would still occur. People would still wake up, work, eat, socialize, and sleep. The fundamentals of existence don't suddenly change because there are two stars overhead. Yet the details would constantly remind you that you're somewhere different. A glance upward would reveal it. A shifting shadow would reveal it. A second sunrise would reveal it. Even the passage of years would feel different. Consider how strongly our own lives are connected to seasonal expectations. We know when spring arrives. We know when summer arrives. We know how daylight changes through the year. Now imagine trying to develop those expectations while two stars continuously move around each other. The resulting patterns become much more intricate, not random, not chaotic, just richer, more layered, more complex. That's one reason astronomers find systems like Kepler-16 so fascinating. They demonstrate how many different versions of normal can exist. Earth teaches us one way a planetary system can operate. Kepler-16 teaches us another. Neither is inherently more natural than the other. They're simply different solutions generated by the same physical laws, and that's one of the recurring themes in modern astronomy. The universe is far more diverse than humanity once believed. For centuries we assumed our solar system might be typical. Then exoplanets arrived. Thousands upon thousands of them. Each discovery revealed new possibilities, different planetary sizes, different orbital arrangements, different stellar environments, different skies. Kepler-16b became one of the most famous examples because the difference is so easy to visualize. You don't need a degree in astrophysics to appreciate two suns. The image speaks for itself. Even a child immediately understands why it's interesting. Two stars where there should be one. Two shadows instead of one. Two sunrises instead of one. The concept is instantly compelling, yet the reality behind it is even more impressive. Not because it looks unusual, because it works. The system is stable. The orbits persist. Gravity keeps everything organized. The stars dance. The planet circles. The cycles continue. Day after day. Year after year. For billions of years. A sky can tell you a great deal about the world beneath it. Here on Earth, people have looked upward for thousands of years and learned how to navigate oceans, predict seasons, tell stories. measure time, and understand their place in the universe. Long before telescopes existed, the night sky served as humanity's first calendar, first map, and perhaps even our first science textbook. Yet for all its beauty, Earth's sky is something we often take for granted. We know what a sunset looks like. We know what a sunrise looks like. We know how the stars appear after darkness falls. Even the changing seasons feel familiar. Winter becomes spring, spring becomes summer, summer becomes autumn. The cycle repeats. A child growing up on Earth quickly learns these rhythms without ever needing them explained. Now imagine growing up somewhere else. Imagine spending your entire life beneath the skies of a world orbiting two suns. How different would your experience be? The answer is fascinating because some aspects would feel surprisingly familiar, while others would be unlike anything humanity has ever experienced. To begin, let's return to our imaginary moon orbiting Kepler-16b. As we've discussed before, the planet itself is a gas giant. There is no solid surface where someone could stand and watch the horizon. So throughout this thought experiment, we'll imagine a large moon orbiting the planet. A moon with oceans, a moon with continents, a moon with an atmosphere. A place where life, at least hypothetically, might be able to exist. From that moon's surface, the sky would immediately feel different. The first difference would be obvious: the giant planet itself. Unlike Earth, which has a relatively modest moon hanging overhead, a moon orbiting Kepler-16b would spend much of its life beneath the enormous presence of its parent planet. Imagine looking upward and seeing a giant striped world many times larger than the moon appears from Earth. It would dominate the sky. Some nights it might fill an enormous portion of the heavens. Cloud bands could be visible. Storm systems might be visible. Its presence would become a normal part of daily life. Children would grow up seeing it overhead and think nothing of it. Visitors would stare at it for hours. But that giant planet would only be part of the spectacle. The stars themselves would create an even more unusual sky. During daylight, the larger star would usually dominate. Kepler-16. A is significantly brighter than its smaller companion. Most of the illumination would come from it. The smaller red dwarf would contribute additional light, but it would not overpower the primary star. As a result, many days might initially seem somewhat familiar, not identical to Earth, but recognizable. Then the geometry would change, because the stars never stop moving. Remember, Kepler-16a and Kepler-16b orbit each other every 41 days. Their positions relative to one another shift continuously. Some days they would appear relatively close together. Other days they would be separated by a greater distance in the sky. The effect would be subtle at times and dramatic at others, and as the stars moved, the appearance of daylight would evolve. Imagine a year-long series of sunsets, no two exactly alike, no single pattern remaining fixed for very long. The sky would constantly offer slight variations. One evening the stars might appear close together as they approached the horizon. Another evening they might set far apart. Sometimes the smaller star could remain visible after the larger one disappeared. Sometimes the reverse might occur. Every sunset would carry a degree of uniqueness. Humans would almost certainly become sky watchers, not because astronomy was a specialized hobby, because the heavens would be too interesting to ignore. Then there is twilight. Twilight on Earth occurs because sunlight scatters through our atmosphere even after the sun dips below the horizon. The process creates familiar transitions. Daylight softens, colors change, darkness gradually arrives. A double-star system complicates this process. Suppose one star sets while the other remains above the horizon. Twilight would not behave the way we expect. Instead of darkness steadily advancing, daylight could linger. The sky might remain brighter than anticipated. Then, when the second star finally disappeared, twilight would begin again. Imagine experiencing two separate twilight phases during the same evening. The quality of light would shift repeatedly. Photographers would probably never stop taking pictures. Artists would never run out of inspiration. Even ordinary walks home from work could feel visually different depending on the positions of the stars. Yet perhaps the most remarkable transformation would occur once darkness finally arrived, because darkness itself would feel different. On Earth, our night sky contains familiar features: the moon, the planets, the Milky Way, thousands of visible stars, ancient constellations. The appearance changes somewhat through the seasons, but the overall structure remains recognizable. A moon orbiting Kepler-16b would offer a very different celestial landscape. For one thing, the giant planet would dominate many nights. Imagine the way our moon appears in Earth's sky. Now increase that apparent size dramatically. The result would be breathtaking. Depending on orbital position, the gas giant could appear enormous. Its cloud bands might become visible to the naked eye. Storm systems could potentially be observed. The sight would be so common that local cultures might build entire mythologies around it. Human history demonstrates that we love assigning meaning to objects in the sky. The moon influenced myths, calendars, religions, and folklore throughout history. A giant planet hanging overhead would likely do the same. It would become part of the culture, part of daily language, part of identity. And beyond that giant world would lie the stars. Lots of them, perhaps more than many people realize. One consequence of living away from the light pollution of modern civilization is that the night sky becomes extraordinarily rich. Many people today rarely see the true Milky Way. Artificial lighting hides much of it. Travel to a truly dark location, however, and the sky transforms. Thousands of stars emerge. Dust lanes become visible. The galaxy stretches overhead like a luminous river. Now imagine that experience beneath an entirely different stellar arrangement. The familiar constellations of Earth would be gone. No Orion, no Big Dipper, no Cassiopeia. Those patterns exist only because of our specific location in the galaxy. Move hundreds of light years away, and the stellar landscape changes. New constellations would emerge, new patterns would be invented, new stories would develop. Ancient astronomers on such a world would create their own celestial traditions. Different heroes, different legends, different interpretations. The stars would remain the same physical objects, but their arrangement would look entirely different. This idea is surprisingly profound. Constellations feel timeless to us, yet they are local phenomena. They belong to our perspective. Move elsewhere, and the sky tells a different story. A civilization beneath the skies of Kepler-16 would create completely different maps of the heavens, different navigational systems, different myths, different astronomy. And then there are the seasons. If the night sky would seem unusual, the seasons could feel downright strange. On Earth, seasons arise primarily because of axial tilt. Our planet's rotational axis is tilted by approximately 23.5 degrees. As Earth orbits the Sun, different hemispheres receive varying amounts of sunlight. The result is familiar: summer, autumn, winter, spring. The cycle repeats every year. Simple, predictable. Kepler-16b introduces additional complexity. Not only does the planet orbit around the stellar pair, but the stars themselves are moving around each other. This means the amount of energy reaching the planet can vary in more intricate ways. Imagine trying to predict temperatures while the sources of sunlight are constantly changing position. The larger star contributes most of the energy. The smaller star contributes less. Their relative arrangement shifts continuously. Sometimes the geometry favors slightly greater illumination, sometimes slightly less. The effect is not extreme enough to throw the system into chaos. The planet remains stable, yet seasonal patterns could become far more complicated than those experienced on Earth. Researchers studying circumbinary systems have found that such worlds can experience seasonal variations unlike anything in our solar system, not because the laws of physics change, because the orbital relationships become more complex. Multiple celestial clocks begin interacting simultaneously. The planet's orbit provides one cycle, the star's orbit provides another. Together they create patterns that can take a long time to repeat exactly. Imagine living in a place where summers are not identical from year to year, where subtle differences emerge depending on the current arrangement of the stars, where long-term climate cycles become more intricate than anything farmers on Earth typically encounter. Civilizations would adapt. They always do. Humans have survived deserts, rainforests, tundra, mountains, and islands. Given enough time, societies learn local patterns. A civilization beneath twin suns would eventually understand its own seasonal rhythms, but those rhythms would likely be more complicated than ours. Calendars might become extraordinarily sophisticated. Astronomers would hold important positions in society. Accurate predictions could matter greatly for agriculture. The sky would become a source of practical information as well as beauty. Interestingly, this brings us back to something humans have done throughout history. Ancient civilizations often relied heavily on astronomy, not because they were obsessed with stars, because survival depended upon understanding cycles. Planting seasons, harvest seasons, flood cycles, navigation, the sky contained useful information. A world orbiting twin suns would probably encourage a similar relationship. People would pay attention. The heavens would matter, perhaps more than they do for many modern societies. And through all of it, the stars would continue their endless dance. One orbit every 41 days, the planet completing its own longer journey around them. Daylight changing, shadows shifting, twilights evolving, the night sky transforming across the year. What makes systems like Kepler-16 so fascinating is not that they break the laws of nature. They don't. Everything follows perfectly ordinary physics. Gravity works exactly as expected. Light behaves exactly as expected. Orbits obey the same rules found throughout the universe. The difference lies in arrangement. Nature has taken familiar ingredients and assembled them differently. The result is a world that feels exotic despite being governed by the same laws that shape Earth. When people first hear about Kepler-16b, they often imagine standing beneath twin suns and immediately begin wondering about the weather. It's a natural question. After all, weather is one of the most personal ways we experience a planet. Most of us rarely think about atmospheric pressure, orbital mechanics, or the physics of radiation during everyday life. What we notice is whether it's sunny or cloudy, whether we need a coat, whether rain is coming, whether summer feels warmer than usual. Weather turns astronomy into something tangible. It's one thing to know that a world exists hundreds of light years away. It's another thing entirely to imagine what it might feel like to stand beneath its sky and experience an ordinary afternoon. Would it be warm? Would it be windy? Would storms behave differently? Would two suns create twice as much heat? And perhaps most importantly, would the weather on a double sun world feel completely alien? The answer, as is often the case in astronomy, is both yes and no. Some aspects would seem remarkably familiar. Others would be unlike anything experienced on Earth. Before we continue, however, we need to remember an important detail. Kepler-16b itself is not a rocky planet. It is a gas giant. That means there is no solid surface where someone could stand with an umbrella while checking the forecast. No beaches, no mountains, no forests, no cities. Instead, the planet resembles Saturn far more than Earth. Its atmosphere gradually becomes denser with depth. Travel downward far enough, and the pressures become extreme. Eventually conditions grow so intense that any ordinary spacecraft would be crushed. So when we talk about weather, we need to imagine one of two possibilities. Either we're discussing conditions within the atmosphere of Kepler-16b itself, or we're imagining a hypothetical moon orbiting the giant planet. Both possibilities are fascinating. Let's begin with the gas giant. If you could somehow observe Kepler-16b up close, one of the first things you'd notice would be its clouds. Gas giants are essentially giant weather systems. Unlike Earth, where oceans, continents and mountains influence atmospheric circulation, a gas giant is almost entirely atmosphere. Clouds stretch for enormous distances. Wind systems can encircle the entire planet. Storms may grow to sizes that would dwarf anything found on Earth. Our own solar system provides excellent examples. Jupiter's Great Red Spot has persisted for centuries. It is so large that Earth itself could fit inside it. Saturn contains massive storms that periodically erupt across huge portions of the planet. Even Uranus and Neptune, despite their greater distance from the Sun, possess surprisingly dynamic atmospheres. Kepler-16b likely experiences similar processes: powerful winds, massive cloud systems, complex atmospheric circulation. The exact details remain uncertain because the planet is so far away. We cannot yet watch its weather in the same way we observe Jupiter's, yet the laws of physics suggest an active atmosphere is highly probable. The atmosphere would be constantly responding to incoming energy from the two stars, and that introduces an interesting complication. Most planets receive energy from a single star. Kepler-16b receives energy from two. At first glance, that sounds as though the planet should be dramatically hotter. Two suns must mean double the heat, right? Not necessarily. This is one of those situations where intuition can be misleading. The amount of energy a planet receives depends on many factors. Distance matters enormously. The brightness of each star matters. The arrangement of the stars matters. A planet orbiting two relatively dim stars can actually be cooler than Earth, and that's essentially what we find with Kepler-16b. The stars in the system are not as powerful as our Sun. Furthermore, the planet orbits at a substantial distance from them. As a result, Kepler-16b is not a scorching desert world. Quite the opposite. Researchers estimate that its equilibrium temperature is roughly minus 100 degrees Celsius. That's cold. Very cold. Colder than the coldest temperatures ever recorded on Earth. Cold enough that water would be frozen solid. Cold enough that many familiar forms of weather would behave very differently. If you somehow stood on a hypothetical moon orbiting Kepler-16b, you would not be worrying about sunburn. You would be worrying about freezing. This surprises many people because the image of twin suns tends to suggest warmth. Our brains associate additional stars with additional heat. Yet nature isn't quite so simple. Two relatively modest stars located far enough away can produce an environment far colder than Earth. In astronomy, appearances can be deceiving. A dramatic sky does not guarantee a comfortable climate. Still, even a cold world can possess fascinating weather. In fact, some of the most interesting weather in our solar system occurs on cold planets and moons. Consider Titan, Saturn's largest moon. Titan experiences rainfall. It has rivers. It has lakes. It has weather systems. Yet those rivers and lakes are not made of water. They're made primarily of liquid methane and ethane. The temperatures are so low that substances we consider gases become liquids. Meanwhile, water behaves like rock. Imagine a landscape where methane falls from clouds the way rain falls on Earth. A place where water is harder than granite. That's Titan, and it demonstrates an important lesson. Weather is not limited to warm environments. Weather simply involves atmospheres moving energy around. Kepler-16b likely does exactly that. The details may differ dramatically from Earth, but the underlying principles remain familiar. Heat enters the atmosphere, winds redistribute energy, clouds form, storms develop, patterns emerge. Nature loves patterns. One particularly interesting aspect of a double sun world involves changing illumination. Remember, the stars orbit each other every 41 days. Their positions constantly shift. As they move, the amount and angle of incoming light changes, not drastically from 1 hour to the next, but enough to matter over longer periods. Imagine living in a place where the primary sources of daylight slowly rearrange themselves throughout the year. The atmosphere would respond, temperatures could vary, cloud patterns might shift, seasonal cycles could become more complicated. Meteorologists on such a world would probably have challenging jobs. Weather forecasting on Earth is already difficult. Now imagine trying to account for 2 moving stars instead of 1. The calculations become considerably more interesting. Of course, if intelligent life existed on a moon in such a system, it would eventually adapt. Humans often assume unfamiliar conditions must be confusing, but every civilization learns the sky it grows up beneath. People living beneath 2 suns would likely find our single-star system equally strange. A child raised under twin suns might ask why Earth's weather seems so simple. Why only one sunrise? Why only one major source of daylight? Why does the sun stay in the same general role all year? To them, our sky could seem oddly uncomplicated. Perspective changes everything, and perspective is one of the gifts astronomy offers repeatedly. It reminds us that what feels normal is often merely local. Earth's weather feels ordinary because it's ours. The weather of Kepler-16b feels exotic because it's distant. Yet both emerge from the same physical laws. Both result from atmospheres interacting with starlight. Both involve energy-seeking balance. The scale differs, the details differ. The underlying principles remain remarkably familiar. Now let's imagine our hypothetical moon again. Suppose this moon possesses oceans. Suppose it has continents. Suppose it has an atmosphere capable of supporting Earth-like weather. What would daily forecasts look like? One immediate difference would involve the appearance of clouds. Clouds are heavily influenced by the direction of incoming sunlight. On Earth, there's one dominant source. On a double-sun world, 2 stars could illuminate cloud formations from different angles. The result might be spectacular. Imagine towering clouds glowing along multiple edges simultaneously. Imagine sunsets painting cloud layers with overlapping colours. Imagine storm systems illuminated by 2 celestial light sources rather than 1. The visual effects could be extraordinary. Even ordinary weather might appear beautiful. Then there are shadows. We touched on this earlier, but weather would make the effect even more noticeable. Cloud shadows crossing the landscape would become more complex. Storm systems could produce layered patterns of light and darkness. A cloudy afternoon might look dramatically different from anything experienced on Earth. Photographers would likely become obsessed. Painters would never run out of material. Even a routine rainstorm might create lighting conditions that seem almost surreal to earthly eyes. Yet weather is not merely about beauty. It's about survival. And that brings us to another fascinating possibility. Long-term climate cycles. On Earth, climate is influenced by countless factors: solar output, ocean currents, atmospheric composition, orbital variations, volcanic activity. The list goes on. A double-star system introduces additional variables. The changing positions of the stars could contribute subtle long-term effects. Over decades or centuries, these cycles might influence climate patterns in ways unfamiliar to us. Not necessarily extreme effects. Nature tends to prefer stability when stability is available, but enough variation to create a more intricate climate system. Astronomers studying circumbinary planets often find themselves thinking about these possibilities, not because we can currently predict every detail. We can't. The systems are too distant, the data remains limited. Instead, researchers explore what physics allows. What kinds of climates are possible? What kinds of weather patterns might emerge? What conditions could support habitability? Kepler-16b itself is unlikely to host life as we know it. Its low temperatures and gaseous nature make that difficult. Yet the questions remain valuable, because other circumbinary planets may prove more hospitable. Kepler-16b opened a door. It demonstrated that stable worlds can exist around 2 stars. Once that door opened, astronomers naturally began asking what else might exist beyond it. Perhaps somewhere in the galaxy, there really is a habitable moon, orbiting a giant planet beneath twin suns. Perhaps clouds drift across its sky right now. Perhaps rain falls there. Perhaps winds carry weather systems across continents, illuminated by two stars. We don't know, and that's part of what makes the subject so enjoyable. The universe remains full of possibilities. Every discovery expands the range of environments we can imagine. Kepler-16b taught us that two-sun worlds are real. The next question became whether those worlds could also be comfortable places to live. Could anyone actually live there? By this point in our journey, it would be easy to fall in love with Kepler-16b. After all, it has everything needed to capture the imagination. Two suns, double sunsets, a sky unlike anything on Earth, complex seasons. A fascinating orbital dance. If someone described the system without mentioning any other details, you might reasonably assume Kepler-16b is one of the most promising places in the galaxy for life. Many people had exactly that reaction when the discovery was announced. The headlines certainly encouraged it. The phrase "real-life Tatooine" appeared everywhere. Images of twin suns filled news articles. Astronomy enthusiasts imagined standing beneath an alien horizon, while two stars slowly crossed the sky. The discovery felt exciting because it seemed familiar. Not familiar in the sense that it resembled Earth. Familiar in the sense that people had already imagined worlds like it for decades. Yet astronomy has a habit of reminding us that appearances can be misleading. Sometimes a world that looks promising turns out to be hostile. Sometimes a place that seems ordinary reveals unexpected surprises. And in the case of Kepler-16b, the reality is considerably less comfortable than the romantic image suggests. The planet is remarkable, it is important, it is scientifically fascinating, but it is almost certainly not another Earth. To understand why, we need to begin with something very simple: the ground, or more specifically, the complete absence of it. When people imagine living on another planet, they usually picture standing somewhere, walking, climbing hills, building houses, looking out over landscapes. Human beings evolved on solid surfaces. Our brains naturally associate the word planet with terrain. Mountains, valleys, oceans, deserts, forests. We think of planets as places where you can stand. Kepler-16b immediately breaks that expectation, because it is not a rocky planet. It is a gas giant. That means there is no conventional surface, no shoreline, no continent, no mountain range, no place where someone could simply land a spacecraft and step outside. This distinction is extremely important. Imagine Jupiter. Now imagine trying to stand on Jupiter. The problem becomes obvious rather quickly. As you descend into a gas giant, the atmosphere becomes denser and denser. Pressure increases continuously. Temperatures change. Conditions grow more extreme. There is no sharp boundary where atmosphere suddenly becomes solid ground. Instead, the atmosphere gradually transitions into deeper and deeper layers. Kepler-16b is similar. A spacecraft entering the atmosphere would not find a convenient landing site. It would simply continue descending into increasingly hostile conditions. Pressure would climb. The environment would become more dangerous. Eventually, the spacecraft would be destroyed. This fact alone effectively removes the possibility of Earth-like life existing directly on the planet. Human beings require stable surfaces. Trees require stable surfaces. Most complex ecosystems require stable surfaces. Kepler-16b offers none. But let's suppose for a moment that we could somehow overlook that problem. Perhaps advanced technology allows floating cities. Perhaps future civilizations build enormous atmospheric habitats. Even then, additional challenges quickly emerge. The next issue is temperature. People often hear two suns and immediately imagine heat. It's an understandable assumption. More stars should mean more warmth. Yet as we discussed previously, Kepler-16b is surprisingly cold. Its estimated equilibrium temperature is roughly minus 100 degrees Celsius. That is approximately minus 148 degrees Fahrenheit. For comparison, Antarctica's coldest recorded temperatures are significantly warmer. The difference is substantial. At those temperatures, liquid water becomes difficult to maintain, and water is extraordinarily important. One of the recurring themes in astrobiology is that liquid water appears to be a key ingredient for life as we know it. Every known living organism on Earth depends upon it. Water acts as a solvent. It transports nutrients. It supports chemical reactions. It helps regulate temperature. Life and water are deeply connected. Remove liquid water and many biological possibilities disappear. Now, to be fair, scientists remain open-minded. Life elsewhere may operate differently. Alien biology could potentially utilize unfamiliar chemistry. The universe is large enough to surprise us. Yet when researchers evaluate habitability, liquid water remains one of the first things they examine, and Kepler-16b does not appear promising in that regard. The planet receives significantly less energy than Earth. The result is a cold environment that would challenge many familiar biological processes. Then there is the atmosphere itself. Gas giant atmospheres are not calm places. If you've ever seen images of Jupiter, you've already witnessed some examples. Gigantic storms, powerful winds, turbulent cloud systems. Enormous atmospheric structures stretching across vast distances. These features are beautiful from afar. They are less appealing when you're trying to survive inside them. Weather on a gas giant can become extraordinarily violent. Wind speeds may reach hundreds or even thousands of kilometers per hour. Storm systems can persist for years. Atmospheric circulation operates on scales that dwarf anything found on Earth. Imagine trying to build a city inside a hurricane. Then imagine the hurricane lasting for centuries. That begins to convey the challenge. Again, this does not make the planet uninteresting. Quite the opposite. Gas giants are among the most fascinating objects in planetary science. But fascinating and habitable are not the same thing. A volcano is fascinating. Living inside one is generally discouraged. The same principle applies here. Kepler-16b is an extraordinary scientific target. It is not an attractive destination for future settlers. Another issue involves gravity. The exact experience would depend on altitude and location within the atmosphere, but gas giants often possess stronger gravitational environments than Earth. Gravity influences everything: movement, circulation, biology, engineering, the design of structures, the behavior of atmospheres. Human bodies evolved under Earth-specific gravitational conditions. Significant deviations can create challenges. Astronauts already experience physiological changes after spending extended periods in microgravity. Likewise, substantially stronger gravity could introduce its own difficulties. A future civilization attempting to inhabit a gas giant would face obstacles from every direction: temperature, pressure, atmospheric turbulence, gravity, the absence of solid ground. The list grows quickly, and we haven't even discussed radiation yet. Now, Kepler-16b is not necessarily a radiation nightmare on the level of some environments astronomers study, but radiation always matters in planetary science. Stars produce it. Space contains it. Magnetic fields influence it. Atmospheres shield against it. Any assessment of habitability must consider it. Earth benefits enormously from its magnetic field and atmosphere. Together they provide substantial protection. Remove those protections and life becomes far more vulnerable. One reason Mars presents challenges for future colonization is its reduced atmospheric shielding and weaker magnetic protection. Kepler-16b introduces an entirely different set of complications. Again, not necessarily insurmountable for hypothetical advanced civilizations, but certainly not ideal. By now, the picture is becoming clear. Kepler-16b fails the another Earth test for multiple reasons. It lacks a solid surface. It is extremely cold. Its atmosphere is hostile. Its environmental conditions are challenging. The planet itself is not a comfortable home for life as we currently understand it. Yet here's where the story becomes more interesting. Because ruling out the planet does not necessarily rule out the system. Astronomers learned this lesson within our own solar system. For a long time, discussions about habitability focused primarily on planets. Venus, Earth, Mars. Simple. Then scientists began studying moons more closely, and everything became more complicated. Europa, Enceladus, Titan, Ganymede, Callisto. Suddenly, moons started looking surprisingly intriguing. Europa contains a vast subsurface ocean. Enceladus ejects water vapour into space. Titan possesses weather systems, rivers and lakes. Not water lakes, admittedly, but lakes nonetheless. These discoveries expanded scientific thinking. Habitability might not be limited to planets. Moons could matter too. And once that realization arrived, Kepler-16b looked slightly different. Not because the gas giant itself became habitable, because researchers began asking a new question. What about moons? Imagine a large moon orbiting Kepler-16b. A moon with sufficient mass to maintain an atmosphere, a moon with geological activity, a moon capable of retaining heat. Could such a place support life? The answer remains unknown. We haven't detected any moons around Kepler-16b yet. Current technology makes such discoveries extremely difficult. But the possibility is scientifically interesting. After all, if giant planets in our solar system can host large moons, perhaps giant planets elsewhere can do the same. A habitable moon orbiting a circumbinary planet would be an extraordinary place. Imagine standing on such a world. The giant planet hangs overhead. 2 suns move through the sky. Complex seasonal cycles unfold across the landscape. The environment might look exotic while remaining physically suitable for life. At the moment, however, this remains speculation. A fascinating possibility, not an established fact. And that's an important distinction. Astronomy often requires patience. Many of the most interesting questions take decades to answer, sometimes centuries. Kepler-16b itself was unknown for billions of years. Then suddenly, within a few years of observation, humanity learned it existed. Perhaps future telescopes will reveal moons. Perhaps they won't. The universe will decide. For now, what we know is enough to draw one clear conclusion. Kepler-16b is not another Earth. It is not a hidden twin of our world. It is not a second home waiting to be discovered. Instead, it is something arguably more valuable. Evidence. Evidence that planetary systems can be arranged in ways we once considered unlikely. Evidence that planets can survive around binary stars. Evidence that nature is far more creative than our assumptions. Sometimes scientific discoveries are important not because they answer questions about life, but because they answer questions about possibility. Kepler-16b belongs to that category. It showed us that worlds can orbit 2 suns. That alone transformed astronomy. Far beyond Earth, beyond the familiar worlds of our solar system, beyond even the distant reaches of the Kuiper Belt, a giant planet circles 2 stars in a slow and steady rhythm. By itself, that statement is already remarkable. A planet orbiting 2 suns was once considered something that belonged primarily to science fiction. Then Kepler-16b was discovered, and suddenly the idea became reality. Yet as we've seen, Kepler-16b itself is unlikely to be a comfortable place for life. It is a gas giant. It lacks a solid surface. Its temperatures are extremely cold. Its atmosphere grows increasingly hostile with depth. As fascinating as it is, it does not resemble Earth. For many planets, that would be the end of the story. Case closed. Interesting discovery. Uninhabitable world. Moving on, but astronomy has a habit of complicating simple conclusions. Because once scientists looked at Kepler-16b and recognized it as a giant planet, Another thought naturally emerged. If the planet itself cannot easily support life, could something nearby do so? Could moons become habitats? Could other circumbinary worlds prove more promising? Could entire ecosystems someday be discovered beneath twin suns? After all, we've encountered this idea before. In fact, some of the most promising locations for life in our own solar system are not planets at all. They're moons. That realization would have surprised many astronomers a century ago. For generations, discussions about life beyond Earth focused almost entirely on planets. Venus, Mars. Perhaps some distant Earth-like world orbiting another star. The assumption seemed reasonable. Earth is a planet. Life exists on Earth. Therefore planets must be the important places. Simple. Then spacecraft began exploring the outer solar system, and suddenly the moons started stealing the spotlight. Europa turned out to possess a vast ocean hidden beneath its icy crust. Enceladus began spraying water into space through enormous geysers. Titan revealed rivers, lakes, weather systems, and a thick atmosphere. Even worlds that initially appeared frozen and lifeless became surprisingly interesting. Scientists began asking new questions. Maybe planets aren't the only places where life could emerge. Maybe moons matter too. And once that door opened, astronomers started looking at giant planets differently. Not merely as destinations themselves, as miniature solar systems. Think about Jupiter for a moment. Jupiter has 95 known moons. Saturn has even more. Many are tiny. Some are enormous. Several are larger than planets once considered important enough to dominate astronomy textbooks. If an alien civilization were observing our solar system from far away, they might find Jupiter's moon Europa more interesting than Jupiter itself, or Titan, or perhaps Ganymede. The giant planet becomes the centerpiece of a family of worlds. Kepler-16b may be similar. We simply don't know yet. Current technology allows us to detect the planet. Detecting moons is much harder. Far harder. Imagine trying to spot a tiny insect flying around an airplane from hundreds of kilometers away. Now make both objects hundreds of light years distant. That's closer to the challenge astronomers face. The planet itself is difficult enough to observe. A moon would be significantly harder. As a result, we do not currently know whether Kepler-16b possesses large moons. There may be none. There may be dozens. There may be a few giant moons larger than Mars. At present, the answer remains hidden. But hidden possibilities are often where science becomes most interesting. Because even without direct evidence, we can ask an important question. If such moons exist, could they support life? The answer turns out to be surprisingly complicated. Let's start with the positive side. A moon orbiting Kepler-16b would immediately inherit one fascinating advantage. It would experience the extraordinary sky of the system. 2 suns, complex orbital cycles, the giant planet hanging overhead. From a purely aesthetic perspective, it would be spectacular. Of course, beauty does not guarantee habitability. Life cares much less about scenery than humans do. Life cares about energy, chemistry, temperature, water, stability. Those factors matter far more than impressive sunsets. So let's examine them one by one. First, a moon would need sufficient mass. This is crucial. Small moons struggle to hold onto atmospheres. Our own moon demonstrates this perfectly. Its gravity is too weak to retain a thick atmosphere for long periods. As a result, it remains largely airless. Without atmospheric protection, surface conditions become much harsher. Temperature swings become extreme. Radiation exposure increases. Weather disappears almost entirely. Life faces serious challenges. A habitable moon would therefore need to be relatively large, not necessarily Earth-sized, but large enough to maintain an atmosphere over billions of years. Fortunately, nature is capable of producing such moons. Ganymede, Titan and Callisto are all substantial worlds. Some are larger than the planet Mercury. A moon around Kepler-16b could potentially achieve similar dimensions. If such a moon formed, it might retain an atmosphere, and an atmosphere changes everything. Atmospheres regulate temperature, transport heat, protect against radiation, enable weather, support complex chemistry. They transform barren rocks into potentially dynamic worlds. The second requirement is energy. Life requires a source of usable energy. On Earth, most ecosystems ultimately depend on sunlight. Plants capture solar energy. Animals consume plants. Predators consume animals. The entire system flows from the sun. Would a moon around Kepler-16b receive enough energy? Possibly. This is where things become interesting. Although Kepler-16b itself is relatively cold, a sufficiently favourable moon could potentially experience more moderate conditions depending on numerous factors. Atmospheric composition matters, orbital characteristics matter, internal heat matters, and that's a key point many people overlook. A world does not rely solely on starlight. Some moons possess internal energy sources. Europa provides an excellent example. Its subsurface ocean remains liquid largely because of tidal heating. Jupiter's gravity stretches and squeezes the moon repeatedly. That constant flexing generates heat. The process works somewhat like repeatedly bending a paperclip. Energy is deposited into the material, heat accumulates, the moon stays warm. A moon orbiting Kepler-16b could potentially experience something similar. The giant planet's gravity might generate tidal heating. If the moon's orbit were slightly elliptical, the effect could become significant. Internal oceans might remain liquid. Geological activity could persist. The world might stay active long after a comparable isolated planet had cooled. This possibility excites astrobiologists, because internal oceans represent one of the most promising environments for extraterrestrial life. They provide liquid water, they provide chemical gradients, they provide long-term stability, and importantly, they can exist even in places where surface conditions are extremely cold. Europa is perhaps the most famous example. Beneath its frozen crust lies a global ocean. That ocean contains more water than all of Earth's oceans combined. Think about that for a moment. A moon smaller than Earth may contain an even larger reservoir of liquid water. If life can emerge in such environments, the universe suddenly becomes much more interesting. A moon around Kepler-16b might possess similar possibilities, not because we know it does, because physics allows it. And when physics allows something, nature often finds ways to surprise us. Then there is the issue of stability. Life benefits from consistency, not necessarily complete predictability, but stability over long periods. Complex organisms require time to evolve. Ecosystems require time to develop. Rapidly changing environments can make this difficult. Fortunately, Kepler-16 itself appears remarkably stable. The planet's orbit has persisted for billions of years. The stars follow predictable paths. Nothing suggests a chaotic system on the verge of collapse. This matters because any moon orbiting Kepler-16b would share that long-term stability. A stable moon around a stable planet in a stable stellar system begins checking important boxes on the habitability checklist. Not all of them, but enough to attract attention. Of course, challenges remain. One major concern involves radiation. Gas giants often possess powerful magnetic fields. Jupiter's magnetic environment, for example, can be extremely hostile. Radiation trapped within its magnetosphere creates dangerous conditions for nearby moons. Europa experiences this problem, so does Io. Any moon orbiting Kepler-16b might face similar difficulties. Excessive radiation can damage biological molecules. It can alter chemistry. It can make surface environments difficult for life. Fortunately, atmospheres and oceans can provide protection. Life beneath water enjoys substantial shielding. Life underground enjoys shielding too. Habitability often depends on details, and details are exactly what we currently lack. Another fascinating possibility involves the existence of multiple moons. Remember, giant planets rarely travel alone. Jupiter possesses an entire family of moons. Saturn possesses an even larger family. If Kepler-16b follows the same pattern, there could be numerous moons orbiting it. Imagine a miniature planetary system beneath twin suns, one moon icy, another volcanic, another covered in oceans, another possessing a thick atmosphere. The giant planet hanging overhead while multiple worlds circle around it. It's a striking image, and perhaps not an unrealistic one. Nature has already produced similar arrangements closer to home. The biggest obstacle is simply that we haven't observed them yet. Technology imposes limits. Even the most powerful telescopes cannot currently reveal every detail of distant planetary systems. Astronomy often proceeds this way. First comes discovery, then comes speculation, then eventually comes improved observation. Questions that seem impossible today become routine tomorrow. A few decades ago, exoplanets themselves remained unconfirmed. Now thousands are known. A century ago, nobody knew galaxies existed beyond the Milky Way. Today, astronomers catalogue millions of them. Knowledge expands, instruments improve, mysteries gradually surrender their secrets. Kepler-16b sits at an interesting point in that process. We know the planet exists, we know its stars exist, we understand much of its orbital architecture, but the moons, if they exist, remain hidden. For now. That uncertainty leaves room for imagination. Not wild fantasy. Scientific imagination. The kind that asks reasonable questions and patiently waits for evidence. Could a moon around Kepler-16b support life? Perhaps. Could it possess oceans? Possibly. Could it maintain an atmosphere? Potentially. Could complex ecosystems develop beneath twin suns? The laws of physics do not forbid it, and that's important. Because some worlds can be ruled out immediately, others remain candidates. Kepler-16b itself appears inhospitable. Its moons, however, occupy a different category. Not confirmed habitats, not confirmed lifeless worlds, possibilities. And in astronomy, possibilities matter. They guide future research. They inspire new missions. They motivate better telescopes. Every major discovery begins with a question. Could planets exist around other stars? Could black holes be real? Could galaxies exist beyond our own? Could life survive beneath ice-covered oceans? Again and again, questions drive exploration. The question of moons around Kepler-16b belongs to that tradition. Perhaps future observatories will finally detect them. Perhaps one day astronomers will identify atmospheric signatures around a moon, orbiting a giant planet beneath two suns. Perhaps future generations will look back at our uncertainty the way we look back at 19th century debates about whether other planets exist. For now, however, we remain at an intriguing midpoint. We know enough to imagine, not enough to conclude, and that balance between knowledge and mystery is part of what makes astronomy so captivating. Because somewhere out there, beyond the reach of current instruments, a moon may already be circling Kepler-16b, its skies illuminated by twin stars. Its seasons shaped by complex celestial rhythms, its landscape entirely unknown. There is something wonderfully human about imagining ourselves in unfamiliar places. Astronomers discover a planet hundreds of light years away, and almost immediately we begin asking questions that have very little to do with orbital mechanics. What would the air feel like? What would the sky look like? What would daily life be like? Could I live there? Could I raise a family there? Could I walk outside after dinner and watch the sunset? These questions appear again and again throughout history. When sailors first crossed oceans, people imagined distant continents. When telescopes revealed other planets, people imagined standing on them. When astronauts reached the moon, people immediately began imagining lunar cities. And when Kepler-16b introduced the world to a genuine planet orbiting two suns, another question naturally emerged. What would it actually feel like to live beneath that sky? Not as a scientist, not as an astronaut, not as an explorer, as an ordinary person, someone who wakes up in the morning, goes to work, comes home in the evening, and occasionally glances upward while wondering whether it might rain tomorrow. Because ultimately that's how humans experience worlds. Not through equations, through everyday life. And if there is one feature that would define daily existence beneath two suns more than any other, it would probably be shadows. That sounds almost trivial at first. Shadows are easy to ignore. Most of us rarely think about them. They simply exist. You walk outside, a shadow follows, a tree casts a shadow, a building casts a shadow. Everything behaves exactly as expected. One sun, one shadow. Simple. Yet that simplicity is something we only appreciate after imagining its absence. Picture yourself stepping outside one morning on a habitable moon, orbiting Kepler-16b. The larger star has already risen. The landscape glows with daylight. You look down. A shadow stretches across the ground, perfectly normal. Then the second star rises, and suddenly your shadow changes. Not because the first one disappears, because a second one appears. Now two shadows accompany you. One darker, one fainter, both moving in slightly different directions, both attached to you, both completely normal for the people who live there. Imagine how strange that would feel during your first few days. Your brain would constantly notice it. You'd stop walking and look down. You'd wave your arm just to watch the shadows move. You'd probably spend an embarrassing amount of time experimenting with them. Children certainly would. Children experiment with everything. Give them two shadows instead of one and entire afternoons would disappear. Games would be invented. Competitions would emerge. Someone would inevitably try to jump on both shadows at once. Human nature rarely changes. Eventually, however, the novelty would fade. That's one of the remarkable things about people. We adapt. The extraordinary becomes ordinary with surprising speed. Consider Earth. We're standing on a rotating planet moving around a star at roughly 30 kilometers per second. The solar system itself is moving through the galaxy. The galaxy is moving through the universe. Objectively speaking, it's all astonishing. Yet most mornings we're more concerned about whether we remembered our keys. Familiarity has a way of normalizing miracles. The same thing would happen beneath twin suns. Visitors from Earth would spend hours staring at the shadows. Residents would barely notice them. The shadows would simply become part of life. And that's where things become particularly interesting. Because once you move beyond the novelty, you begin realizing how many small aspects of civilization would develop differently. Architecture, for example. Here on Earth, buildings are designed around one primary source of sunlight. Architects think about where the sun rises, where it sets, how light enters rooms, how shadows fall across courtyards. A world with two suns would complicate those calculations. Windows might be positioned differently. Public spaces might be designed to account for shifting patterns of illumination. Shaded areas could behave in unfamiliar ways. Imagine sitting beneath a tree. On Earth, a tree provides fairly predictable shade. Under twin suns, the same tree might produce overlapping regions of darkness and partial darkness. The experience would feel subtly different, not dramatically, just enough to notice. The same principle applies to entire cities. Urban planners would learn how twin-star illumination affects daily life. Public squares might be oriented toward particularly beautiful celestial alignments. Observatories could become cultural landmarks. Important holidays might coincide with notable stellar configurations. After all, human societies have always paid attention to the sky. We build calendars around it. We organize festivals around it. We tell stories about it. The sky becomes part of culture. It always has. A civilization beneath twin suns would likely develop traditions that seem unusual to us. Imagine a holiday celebrating the day both stars appear closest together in the sky, or a festival marking a particularly dramatic double sunset. Perhaps entire mythologies would emerge around the relationship between the two suns. One might be associated with strength, the other with wisdom, one with summer, the other with winter. Human cultures excel at assigning meaning to celestial objects. We've done it throughout history. The moon inspired myths, the sun inspired religions, planets inspired stories. Two suns would almost certainly inspire their own traditions. And then there is language. Language often reflects environment. People living in snowy regions develop detailed vocabulary for snow. Sailors develop specialized terms for the sea. Astronomers develop specialized terms for the sky. A civilization living beneath two stars would likely possess words that don't exist on Earth. Words describing specific lighting conditions. Words describing particular shadow patterns. Words describing stellar alignments. Expressions that make perfect sense locally but sound odd to visitors. Think about how often we reference the sun in everyday speech. We talk about sunrise, sunset, sunlight, Sundays, sunny weather. A world with two suns might develop entirely different linguistic habits. Language would adapt just as architecture adapts. Culture would adapt. Daily routines would adapt. And perhaps most fascinating of all, people's psychology would adapt. Human beings are deeply influenced by their environments. The sky matters more than we sometimes realize. For thousands of years, Earth's day-night cycles shaped human behavior. It influenced sleep patterns, work schedules, religious practices, social gatherings, even emotional experiences. Sunrise feels hopeful, partly because we've evolved to associate it with a new day. Sunset feels reflective, partly because it signals closure. Now imagine growing up with two suns. Would people experience sunrise differently? Would they feel differently about daylight? Would the sky influence their emotional lives in ways we can't fully predict? It's certainly possible. The environment always leaves fingerprints on culture. And a double-star sky would be one of the most influential environments imaginable. Consider childhood. Many of our earliest memories involve looking upward, watching clouds, watching sunsets, watching stars. Children naturally become fascinated by the sky. Now imagine being a child beneath two suns. You would never know anything else. Every drawing of the sky would include two stars. Every picture in every textbook would show two suns. Every storybook illustration would include twin shadows. The concept of a single sun sky would seem strange, perhaps even incomplete. A child from Earth visiting such a world would ask endless questions. A local child would ask equally endless questions about Earth. Only one sun? Just one? Doesn't that get boring? It's a humorous thought, but it highlights an important point. Normal is relative. What feels natural depends largely on what you're accustomed to. This becomes especially apparent when we consider time. Throughout this series, we've repeatedly encountered the idea that celestial motion shapes calendars. On Earth, one orbit around the Sun defines a year. One rotation defines a day. Simple, reliable. The inhabitants of a habitable moon orbiting Kepler-16b would organize time differently. Not because they enjoy complexity, because their sky demands it. The star's 41-day orbital cycle would be impossible to ignore. People would notice it, track it, build calendars around it. Generations would grow up understanding patterns that seem unfamiliar to us. Astronomers would become important cultural figures, perhaps not because the science itself is difficult, because the sky directly affects daily life. When celestial cycles become visible and obvious, people pay attention. Human history proves this repeatedly. The ancient Egyptians paid attention. The Maya paid attention. The Babylonians paid attention. Every civilization that depended on environmental cycles became interested in astronomy sooner or later. A double-star civilization would likely be no different. And then there are evenings. Imagine finishing work after a long day. You step outside. The giant planet hangs overhead. One sun has already set. The second remains visible. The sky glows with colours unfamiliar to Earth. Clouds reflect light from unusual angles. Shadows gradually soften. Darkness approaches in stages. Perhaps you sit outside with friends. Perhaps you walk alone. Perhaps you simply watch the stars emerge. Ordinary moments would feel slightly extraordinary, not because people would constantly be amazed by them, because beauty often becomes woven into routine. Think about mountain towns on Earth. Residents eventually stop noticing spectacular landscapes. Tourists never stop noticing. The scenery doesn't become less impressive. People simply become accustomed to it. Life beneath two suns would probably work the same way. Residents would carry groceries, attend school, pay taxes, complain about the weather, go to work, all beneath one of the most remarkable skies imaginable. Normal life would continue, because normal life always continues. And perhaps that's the most interesting realization of all. When we imagine alien worlds, we often focus on the dramatic features: twin suns, double shadows, exotic skies. Yet daily existence is usually built from smaller things. Conversations, meals, friendships, routines, the background changes, life continues. A person living beneath two suns might spend very little time thinking about the fact that their world is extraordinary. They would simply live there, just as we live here. And that perspective reveals something important about Kepler-16b itself. For all its strangeness, for all its differences, it remains governed by familiar laws. Gravity works, light travels, orbits persist. The universe is not divided into ordinary places and magical places. It's one continuous reality expressing itself in different ways. Kepler-16b is one expression. Earth is another. When astronomers announced the discovery of Kepler-16b in 2011, the reaction was immediate. Scientists were excited. Journalists were excited. Science fiction fans were excited. Even people who normally paid little attention to astronomy found themselves intrigued by the idea of a real planet orbiting two suns. For a brief moment, it felt as though Kepler-16b occupied a category entirely by itself. A strange exception, a cosmic oddity, a rare curiosity hiding among the stars. That perception didn't last very long, because once astronomers knew such worlds could exist, they immediately began wondering whether Kepler-16b was unique. And if there is one lesson that astronomy teaches repeatedly, it is this. Whenever you discover something once, the next question is always whether you've discovered it many times. History is full of examples. The first asteroid led to the discovery of thousands. The first exoplanet led to the discovery of thousands more. The first black hole candidate eventually became one member of a much larger population. Nature rarely creates only one example of something that works. If a particular arrangement is stable, if physics allows it, chances are the universe has produced it again and again. Kepler-16b raised exactly that possibility. Perhaps it wasn't an exception. Perhaps it was merely the first member of a larger family. As it turns out, that suspicion was correct, and in the years following its discovery, astronomers began finding more planets orbiting twin stars. One by one they emerged from the data collected by the Kepler Space Telescope. Each new discovery told the same basic story. Kepler-16b was not alone. The universe had been building double-sun worlds all along. Humanity simply hadn't known where to look. This realization was enormously important. The first discovery of any new category is exciting. The second discovery is often even more significant. The reason is simple. One example can sometimes be dismissed as unusual. 2 examples suggest a pattern. 3 examples suggest a population. By the time multiple circumbinary planets had been identified, astronomers could no longer treat Kepler-16b as a cosmic accident. Something larger was happening. The galaxy clearly knew how to build these systems, and it knew how to build them repeatedly. One of the next famous discoveries was Kepler-34b. Like Kepler-16b, it orbited 2 stars, yet the system looked quite different. The stars themselves differed, the planet differed, the orbital arrangement differed. Immediately, researchers learned an important lesson. There wasn't just one kind of double-sun world, there were many. Nature was not following a single blueprint, it was experimenting. Kepler-35b soon followed, then Kepler-38b, then Kepler-47, then additional systems beyond those. Each discovery expanded the family tree. Each discovery provided new information. And perhaps most importantly, each discovery challenged assumptions. Before Kepler-16b, many scientists wondered whether binary star systems might be poor environments for planet formation. After all, 2 stars create a complicated gravitational environment. Young planets could be disrupted. Dust disks could be disturbed. Collisions might become destructive rather than constructive. Theoretical models offered mixed predictions. Then observations arrived, and observations have a way of settling arguments. The planets existed, not in simulations, not in equations, in reality, orbiting real stars, following real paths, surviving for immense periods of time. That forced researchers to reconsider their understanding of planetary formation. Perhaps binary systems weren't hostile after all. Perhaps they were merely different. This distinction matters. Astronomy often progresses by replacing assumptions with evidence. For decades, scientists had only one example of a planetary system, our own. Naturally, they used it as a reference point. 1 star, several planets, relatively stable architecture, reasonable. The problem was that nature never promised our solar system was typical. That assumption belonged to us, not to the universe. As more exoplanets were discovered, astronomy entered a period of continuous surprise. Hot Jupiters appeared, super-Earths appeared, mini-Neptunes appeared, planets larger than expected, planets smaller than expected, planets orbiting dead stars, planets orbiting binary stars. Every year seemed to introduce new possibilities. Kepler-16b became part of a much larger revolution, a revolution centered around a simple realization. Planetary systems are incredibly diverse. If you could somehow travel throughout the Milky Way and visit thousands of planetary systems, you would quickly discover that Earth is only one solution among many. Our system works, but it isn't the only design available. The universe appears remarkably creative. Imagine a cosmic architect with unlimited building materials. Instead of constructing the same house repeatedly, the architect experiments. Different layouts, different structures, different combinations. Some systems contain giant planets close to their stars. Some contain compact families of rocky worlds. Some contain multiple stars. Some contain arrangements that continue to puzzle astronomers today. Kepler-16b revealed that binary star architecture belongs on that list, and once scientists began finding additional examples, the implications became increasingly profound. One obvious implication concerned habitability. If planets can exist around binary stars, then potentially habitable worlds might exist around binary stars as well. Notice the difference. We're no longer discussing Kepler-16b specifically. As we've already seen, Kepler-16b itself is unlikely to resemble Earth, but the broader category matters. Imagine a rocky planet orbiting 2 stars at the correct distance. Imagine moderate temperatures, liquid water, a stable atmosphere. Could such a world exist? The answer appears to be yes, at least in principle. And that realization dramatically expanded the range of environments scientists considered potentially interesting. Before circumbinary planets were discovered, habitable worlds around twin stars remained largely theoretical. Afterward, they became legitimate scientific targets. Researchers began running climate models. They began studying orbital stability. They began asking how life might adapt to multiple suns. The discovery of Kepler-16b did not merely reveal one planet, it opened an entirely new field of investigation. That's often how scientific breakthroughs work. The most important discoveries are not necessarily the ones that answer questions. They're the ones that create new questions. Kepler-16b belongs firmly in that category. Another fascinating consequence involved the public's perception of astronomy. People often assume that scientific discoveries become less exciting as they become more common. In some cases that's true, but not always. Circumbinary planets provide an interesting example. The first one captured attention because it was unprecedented. Subsequent discoveries didn't reduce the wonder, they increased it. Each new system reinforced the same extraordinary message. The universe is full of places we never expected. A single double-sun world is remarkable. A growing population of them is transformative. It changes how we think about the galaxy itself. For centuries, people imagined the Milky Way as a vast collection of stars. Then we learned many stars host planets. Then we learned some stars come in pairs. Then we learned those pairs can host planets too. The result is a galaxy that feels increasingly alive with possibility, not necessarily alive in the biological sense, alive with diversity, alive with complexity, alive with unexpected arrangements. Somewhere out there, countless skies exist that no human has ever seen. Some possess one sun, some possess two, some may possess even more. Imagine standing on a world orbiting a binary star. Twin shadows stretch across the ground. The stars move through the sky in an unfamiliar dance. The seasons follow patterns unlike those of Earth. For generations, such imagery belonged primarily to fiction. Now it belongs to astronomy. That transition from imagination to evidence remains one of the most satisfying aspects of the Kepler story. Reality proved capable of matching the dream. Not perfectly. Not in the exact way storytellers envisioned. Reality rarely cooperates that neatly, yet it came surprisingly close, and it continues to do so. Because the discovery of circumbinary planets did not end with Kepler. New instruments continue searching. New surveys continue collecting data. New telescopes continue expanding our view of the galaxy. Every improvement increases the chances of finding additional examples. Some may resemble Kepler-16b, others may look entirely different. Perhaps future discoveries will reveal rocky double-sun worlds. Perhaps they will reveal ocean worlds. Perhaps they will reveal environments stranger than anything currently imagined. History suggests caution whenever we assume we've seen everything. Astronomy has a habit of proving otherwise. Think about how much has changed in just a few decades. In the early 1990s, no exoplanets had been confirmed around Sun-like stars. Today, thousands are known. Entire catalogues exist. Researchers study planetary populations the way biologists study ecosystems. The field has evolved with astonishing speed. Circumbinary planets are part of that story. They remind us how rapidly knowledge can grow. One generation grows up assuming something may be impossible. The next generation studies multiple examples of it. That's a remarkable transformation, and it highlights an important truth about science. Scientific understanding is not a static collection of facts, it's a process. Questions become investigations, investigations become discoveries, discoveries become new questions. The cycle continues. Kepler-16b entered astronomy as an answer. Can planets orbit two stars? Yes. Then it immediately became a question. How many exist? How do they form? Can they support life? What kinds of climates do they possess? What kinds of moons orbit them? The discovery solved one mystery and generated dozens more. And that's exactly what good discoveries tend to do. By now, researchers no longer view double-sun planets as exotic impossibilities. They are recognized as a legitimate category of world, an established part of the galactic inventory. The family continues to grow, and every new member teaches us something. Yet perhaps the most important lesson does not concern any individual planet. It concerns planetary formation itself. Because once astronomers realised that worlds could emerge and survive within binary star systems, they were forced to rethink one of the most fundamental questions in planetary science. How does nature build planets in the first place? A discovery becomes truly important when it changes the way people think, not merely when it adds a new object to a catalogue, not merely when it generates headlines, not merely when it provides an interesting fact to remember. The most significant discoveries force scientists to reconsider assumptions they didn't even realise they were making. Kepler-16b belongs firmly in that category. When the planet was announced in 2011, much of the public focused on the obvious attraction. 2 suns, twin sunsets, a real-world version of an idea that had existed in stories for decades. Those aspects were certainly fascinating. Yet among astronomers, another conversation was taking place, a deeper one, because Kepler-16b was not simply teaching us about one planet, it was teaching us about how planets form in general, and that lesson turned out to be surprisingly profound. To understand why, let's travel backward in time, not a few years, not a few centuries, several billion years. Long before Kepler-16b existed as a mature world, long before its twin stars settled into the stable arrangement we observe today, long before any planet completed a single orbit. Back to the beginning. Every planetary system starts in roughly the same way. A giant cloud of gas and dust drifts through space. These clouds are enormous. Many are dozens or even hundreds of light years across. From a distance they appear calm, beautiful, peaceful. Yet deep inside them, gravity is constantly at work. Tiny irregularities develop. One region becomes slightly denser than another. That denser region exerts slightly stronger gravity. It begins pulling in more material. As more material accumulates, gravity strengthens. The process accelerates. Eventually, entire sections of the cloud collapse inward. Stars begin to form. This process is responsible for nearly every star in the galaxy. Our Sun formed this way. The stars of Kepler-16 formed this way. Countless billions of others form this way. Gravity acts as the great organizer. It takes diffuse material and assembles it into structured systems. Yet the process rarely produces perfect simplicity. People sometimes imagine stars forming individually, each isolated inside its own private cloud. Reality is often messier. Many stellar nurseries produce multiple stars at once. Instead of one star emerging, 2 form, or 3, or even larger groups. This is particularly important for understanding Kepler-16, because its story begins not with a single newborn star, but with 2. As the original cloud collapsed, 2 major concentrations of material emerged. One eventually became Kepler-16a. The other became Kepler-16b. Almost immediately their futures became linked. Gravity bound them together. They began orbiting a shared centre of mass. The binary system was born. And at that point, many astronomers once assumed planet formation might become difficult, perhaps even impossible. The concern was reasonable. Imagine you're trying to build a house. Construction is already complicated. Now imagine the ground beneath you constantly shifts. The materials keep moving. The environment remains unstable. Building becomes harder, not necessarily impossible, just more challenging. Many researchers suspected binary star systems might create similar problems. Young planets begin as tiny particles. Dust grains collide. They stick together. Larger grains form. Pebbles form. Rocks form. Eventually, after countless collisions, larger bodies emerge. This process requires a certain degree of stability. Objects must survive long enough to grow. The problem is that 2 stars create a much more dynamic gravitational environment than one. Instead of a single dominant source of gravity, there are 2. Both move continuously. Both influence the surrounding disk. Both alter the trajectories of nearby material. For decades, scientists debated what that might mean. Some models suggested planet formation would still work. Others suggested difficulties. Certain simulations indicated that collisions could become more violent. Instead of objects merging, they might shatter. Instead of growing, they might be destroyed. Theoretical studies produce mixed results, and that is one of the reasons Kepler-16b became so important, because nature eventually provided an answer, not through speculation, not through simulation, through existence. The planet was there, real, stable, orbiting 2 stars. Immediately, that fact established something crucial. Whatever difficulties binary systems create, they are not insurmountable. Nature had solved the problem, somehow. The challenge then became figuring out how. This is one of the most enjoyable aspects of science. Sometimes discoveries answer questions, sometimes they create mysteries. Kepler-16b did both simultaneously. Astronomers learned that planets can form around binary stars. Wonderful. But how exactly did this particular planet accomplish it? That question triggered years of investigation. Researchers began revisiting their models. They examined planetary disks around binary stars. They studied how material behaves under complex gravitational influences. They explored new formation scenarios. Gradually, a more detailed picture emerged. One possibility involves distance. Remember that Kepler-16b does not orbit extremely close to its stars. It remains safely beyond the most chaotic regions of the system. This may be important. The inner portions of a binary system can experience stronger gravitational disturbances. Material there faces greater challenges. Farther out, conditions become calmer. Not calm by everyday standards, calm by astronomical standards. The distinction matters. Imagine a stormy ocean. Near the center of the storm, waves become violent. Farther away, conditions improve. Similarly, the outer regions of a protoplanetary disk may provide safer environments for planetary growth. Dust accumulates, objects collide, planets gradually emerge. Once formed, they can migrate inward or outward through interactions with the surrounding disk. Planet formation is not a static process. Young planets move, they interact, they evolve. The final arrangement we observe today may differ significantly from the original arrangement billions of years ago. In fact, this idea has become increasingly important throughout planetary science. Astronomers once imagined planets forming exactly where they currently reside. Modern research suggests reality is often more complicated. Many planets migrate. Some travel enormous distances. The giant planets in our own solar system may have shifted positions early in their history. The same could be true for Kepler-16b. Perhaps it formed farther away. Perhaps it migrated. Perhaps multiple mechanisms contributed. The details remain subjects of active research. What matters is that the discovery forced scientists to take these possibilities seriously. Before Kepler-16b, certain theoretical pathways seemed speculative. Afterward, they became necessary. Reality had demonstrated that planet formation in binary systems occurs. Theory needed to explain why. This relationship between observation and theory lies at the heart of science. Observations reveal what exists. Theories attempt to explain it. When the two disagree, theories must adapt. Nature does not negotiate. If a planet exists, it exists. Scientists must figure out how. And Kepler-16b was hardly finished teaching lessons. As additional circumbinary planets were discovered, researchers began noticing something interesting. Many of these systems appeared surprisingly orderly, not chaotic, not unstable. Orderly. That observation challenged another assumption. People often equate complexity with disorder. 2 stars seem more complicated than 1, therefore the system should be more chaotic. Reasonable. Yet the universe repeatedly demonstrates that complexity and stability are not opposites. A galaxy contains hundreds of billions of stars. Yet galaxies exhibit structure. A hurricane contains immense complexity, yet follows physical laws. An ecosystem contains countless interacting organisms, yet can remain stable for long periods. Binary star systems belong to this category. Complicated does not mean impossible. Complicated does not mean unstable. Sometimes complicated systems simply organize themselves differently. Kepler-16b revealed exactly that. The system works, not despite physics. Because of physics, gravity creates order from complexity, again and again. This realization expanded scientific thinking beyond binary stars themselves. Researchers began asking broader questions. If planets can form around binary stars, what other environments might support planetary formation? Could planets exist around triple star systems? Could they form around exotic stellar remnants? Could they survive circumstances once considered unlikely? The answer increasingly appears to be yes. Nature is extraordinarily adaptable. Planet formation is extraordinarily adaptable. Given enough material and enough time, the universe seems remarkably capable of building worlds. That's one of the most important lessons Kepler-16b teaches. For many years, astronomy focused heavily on finding Earth-like systems, a sun-like star, Earth-like planets, Earth-like arrangements. The goal was understandable. Earth is the only known inhabited world. Naturally, researchers wanted to identify similar environments. Yet the exoplanet revolution gradually revealed something unexpected. The universe does not seem particularly interested in copying Earth. Instead, it generates diversity. Lots of diversity. Super-Earths, mini-Neptunes, hot Jupiters, water-rich worlds, binary star planets. Each discovery expands the range of possibilities. Each discovery reminds us that our solar system represents only one example among countless others. Kepler-16b became an ambassador for that idea. It showed that planetary formation is not a fragile process requiring perfect conditions. It is robust, flexible, creative. The universe can build planets under circumstances that once seemed unfavourable. And if it can build planets around binary stars, perhaps it can build them in many other places too. This perspective has important implications for life beyond Earth. Notice that we're not claiming Kepler-16b itself supports life. We've already discussed why that seems unlikely. The lesson is broader. Every time astronomers discover a new category of planetary system, the number of potential habitats increases. Not necessarily confirmed habitats, potential habitats. The distinction matters. Imagine searching for life while assuming planets can form only around single stars. Your search area becomes limited. Now imagine learning that planets also form around binary stars. Suddenly, entire new populations of worlds become relevant. The galaxy grows larger, possibilities multiply. This is one reason exoplanet discoveries excite researchers so much. Every new type of planetary system expands the map. Not literally, the planets were always there. The expansion occurs in our understanding. Kepler-16b helped redraw that map, and perhaps its greatest lesson involves humility. Astronomy repeatedly reminds us that assumptions are dangerous, not because assumptions are foolish, because the universe is larger than our intuition. Humans evolved on one planet, around one star, inside one planetary system. Our instincts reflect that experience. When something differs dramatically from Earth, it can initially seem unlikely. Then observations arrive, and reality proves more imaginative than expected. Again and again, astronomy follows this pattern. The Milky Way was once thought to be the entire universe. It wasn't. Planets around other stars were once hypothetical. Now thousands are known. Double-sun planets once belonged primarily to fiction. Now they belong to astronomy. Kepler-16b sits at the centre of that transition. A world that forced scientists to reconsider what planetary systems can be. a world that demonstrated the adaptability of planet formation, a world that revealed how little we truly knew about the diversity of the galaxy. Eventually, every journey reaches a quiet moment, not necessarily an ending, not necessarily a conclusion, simply a place where we pause for a while and look back at where we've been. Over the course of this exploration, we've travelled more than 200 light years from Earth to visit a world that most humans had never heard of until recently. We've watched two stars orbit each other. We've imagined double sunrises. We've followed giant shadows across alien landscapes. We've explored unusual seasons, strange weather, and the possibility of moons circling a giant planet beneath twin suns. We've discussed gravity, planetary formation, astronomy, and the remarkable flexibility of nature itself. And now, as the stars slowly sink toward the horizon one final time, it is worth asking a simple question. What did Kepler-16b really teach us? At first glance, the answer seems obvious. It taught us that planets can orbit two stars. That was the headline. That was the discovery. That was the fact that captured the world's attention. And certainly that lesson matters. For thousands of years, humanity looked up at the sky and saw only one sun. Every generation inherited the same experience. One star governed the day, one star determined the seasons, one star shaped life itself. The possibility of two suns belonged largely to stories. Then astronomy transformed the story into reality. Kepler-16b proved that worlds orbiting twin stars are not merely possible. They exist. That alone makes the planet historically important. Yet discoveries often become more meaningful with time. The first impression fades. The deeper lessons emerge. And the deeper lessons of Kepler-16b extend far beyond two stars, because when astronomers first began searching for exoplanets, they naturally started with familiar assumptions. The logic made sense. Earth exists. Earth supports life. Earth orbits a single star. Therefore, systems resembling our own seem like the most promising places to look. Nobody was being unreasonable. Science usually begins with known examples. The challenge is that nature rarely limits itself to known examples. The universe is under no obligation to repeat Earth, or the solar system, or anything else we happen to find comfortable. And Kepler-16b became one of the earliest reminders of that reality. It showed that our cosmic neighbourhood is not a template. It is one possibility among many. Imagine visiting an enormous city while having previously seen only a single house. You might assume all buildings resemble that house. The kitchen belongs here, the bedroom belongs there, the roof looks like this, the windows look like that. Then you arrive in the city and discover thousands of architectural styles, some familiar, some completely unexpected. The house was not wrong. It was simply one example. That is increasingly how astronomers view the solar system, not as a standard design. As one design, one arrangement among countless others. Kepler-16b helped establish that perspective, and that perspective continues to reshape astronomy today. Every year, telescopes reveal new worlds. Some resemble Earth, some resemble Neptune, some resemble nothing we anticipated. The diversity is extraordinary. And perhaps that's one reason discoveries like Kepler-16b resonate so strongly with people. Not because everyone understands orbital mechanics. Not because everyone studies astrophysics. Because the discovery appeals to something deeply human. Curiosity. We like knowing that reality is larger than expected. Children demonstrate this constantly. Show a child a hidden room in a house, and they immediately want to explore it. Reveal a secret path through a forest, and they want to know where it goes. Humans possess a natural attraction to possibilities. The universe rewards that attraction repeatedly. Just when we think we've mapped the territory, something new appears. Another planet, another moon, another galaxy, another surprise. Kepler-16b belongs to that tradition. For centuries, the idea of a double-sun world existed primarily in imagination. Then astronomers found one, and shortly afterward they found more. The dream became a category, the exception became a population, the story became reality. That transformation is worth appreciating, because it illustrates something important about the relationship between imagination and science. People sometimes treat them as opposites. Imagination invents, science measures, imagination dreams, science tests. Yet history suggests the relationship is far more cooperative. Imagination often asks questions long before science can answer them. Could there be worlds beyond Earth? Could there be multiple suns? Could there be life elsewhere? Could there be planets around other stars? Human beings imagined such possibilities for generations. Eventually technology caught up. Evidence arrived. The questions became investigations. Kepler-16b stands at the intersection of those two traditions. A world once imagined, a world eventually discovered, a world reminding us that curiosity often arrives before confirmation. And perhaps that lesson feels especially relevant today, because despite everything we've learned, we're still living in the early days of exoplanet science. That may sound strange given how much progress has been made. Thousands of planets have been discovered, entire catalogues exist, sophisticated models explain planetary formation, powerful telescopes analyse distant atmospheres. Yet compared to the future, we're only beginning. Think about astronomy in the year 1900. At that time, nobody knew whether planets existed around other stars. The question remained open. Now fast forward to today. The situation has changed dramatically. Imagine another 100 years of progress, or 200, or 500. Future astronomers may possess instruments capable of studying worlds in extraordinary detail. They might observe cloud systems on distant planets, map continents, analyze oceans, monitor weather, detect signs of biology, perhaps even identify civilizations. The possibilities are difficult to predict. History suggests one thing, however. Future discoveries will almost certainly surprise us. They always do. And that brings us back to the sky of Kepler-16b. Imagine for a moment that our hypothetical habitable moon actually exists, not because we've detected it, because the thought experiment is useful. Imagine standing there, the giant planet hangs overhead. The atmosphere is calm, the day is ending. One star approaches the horizon, then the second. Twin shadows stretch across the landscape. Light softens, colours shift. The stars continue their endless dance. You watch the sunset. Not as a scientist, not as an astronomer, simply as a person. At that moment, would you spend much time thinking about orbital mechanics? Probably not. Would you calculate stellar masses? Likely not. Would you contemplate planetary formation models? Perhaps only if you happen to be a very dedicated astrophysicist. Most people would simply enjoy the view, and that's important to remember. Scientific discoveries often begin with measurements. They often end with perspective. The numbers matter. The calculations matter. The observations matter. But ultimately, astronomy is about understanding our place in a larger reality. Every new world expands that reality. Every discovery broadens the horizon. Kepler-16b did exactly that. It reminded us that the universe contains arrangements we never expected. And perhaps more importantly, it reminded us that those arrangements are real. Somewhere out there, two stars genuinely orbit one another. A giant planet genuinely circles both. The system exists whether humans observe it or not. It existed before telescopes, before civilizations, before history. And it will likely continue long after our own era becomes a small footnote in the story of the cosmos. There is something comforting about that. The universe feels vast because it is vast. It feels ancient because it is ancient. Yet despite those immense scales, we have reached a point where we can discover worlds hundreds of light years away. Think about how remarkable that truly is. A species that evolved on one small planet has learned to detect another planet orbiting two distant stars. Not by visiting, not by touching it, simply by studying light. Tiny variations in brightness travelled across hundreds of light years. Sensitive instruments recorded them. Scientists analysed them, and from those subtle signals emerged an entirely new world. That achievement says something about the universe, but it also says something about us. Humans are curious creatures. We build questions, then we build tools, then we use those tools to pursue answers. Again and again, generation after generation, the process never really stops. Kepler-16b represents one moment in that larger story, a milestone, a reminder, a promise, a reminder that the universe remains more creative than our assumptions, a promise that many discoveries still await. And perhaps that's the most appropriate thought to carry with us as the second sun finally disappears beyond the horizon. Because astronomy rarely ends with certainty. Every answer leads to another question. Every map reveals unexplored territory beyond its edges. Every discovery opens new doors. Kepler-16b taught us that planets can orbit two suns. Then it taught us that such worlds are not unique. Then it taught us that planetary formation is more adaptable than expected. And somewhere beyond those lessons lie countless others we haven't yet uncovered. The stars continue moving. The planets continue orbiting. The galaxy continues evolving. Meanwhile, here on Earth, new telescopes are being built. New missions are being planned. New generations of astronomers are growing up beneath a single sun, while preparing to study worlds with two. The story continues. The search continues. The discoveries continue. And somewhere in the darkness beyond our familiar sky, Kepler-16b keeps circling its twin stars, following the same path it has followed for billions of years, waiting quietly while humanity learns, one discovery at a time, just how extraordinary the universe can be.